I became a roboticist in the very beginning of my studies because I cared about artificial intelligence. But rather than studying in a vacuum, I wanted to build something that moves. So when you code and write a program, you could actually honestly see what would happen in the physical world.
We feel really passionately about the robotics nano degree from Udacity. Nowhere else are you going to learn the types and quantity of skills in a practical way in such a compressed time frame.
So in my head, robot is like a big term, but really it's about sensing the world and then thinking about it and deciding what action to take and then taking an action affecting the world in some way.
Now robotics is pervasive. You have robotics in space, in toys, in your home, and things that don't even look like robots, like your entire house, are becoming roboticized. Go to a modern surgery room in a hospital and you find robots assisting surgeons doing surgery.
There are even a lot of companies that are not traditionally robotics companies and have traditionally existed in other areas that are entering the robotics space and are hiring roboticists. They're building their own teams.
You know, the future of robotics is going in a direction about helping people, helping society.
I can tell you there's a huge shortage of roboticists and this field is growing very massively.
You don't have to feel like you have to be able to do everything. You can actually become a mechanical engineering expert on a robotics project or, computer science expert in a robotics project. So from that point of view, the field is big, but you could be almost anyone to contribute to the society.
One of the great things about the Robotics Nano Degree program is that it really prioritizes project experience in a very practical way. And we want to make sure that when you do this program, you leave with the skills to actually enter industry and do real projects that are actually going to ship.
At Udacity, we build nano degree programs like this one to find your job, and we work with leading industry partners, in our case, companies like Lockheed Martin, Bosch, and Uber ATG, to really build curriculum that empowers you to get a job in those industries. And more importantly, you learn stuff you wouldn't expect you'd be learning. Have fun.
Hi, I'm Ryan, and I'll be helping you navigate through this nano degree program. You and I will be learning together how to build awesome robotics software applications, and later we'll get a chance to work hands-on with hardware. So let's get started by meeting your instructors, 3 brilliant roboticists from a company called Electric Movement here in Silicon Valley, where they build awesome robots every day. Hey Thomas.
Hey Ryan.
Thomas is a software engineer here at Electric Movement, specializing in dynamics and computer simulation. So Thomas, maybe you could tell students what topics will be covered in the first term of the program.
Sure. You'll start by diving straight into a project where you'll get first-hand experience in the 3 essential elements of robotics: perception, decision-making, and actuation. After that, you begin using the robot operating system to build awesome robotics applications. You'll develop your knowledge in the areas of kinematics, control, computer vision, and even deep learning for robotics.
Super cool. Hey Harsh, how's it going?
Hey Ryan, it's going well.
Harsh is a robotics software engineer here at Electric Movement. He's really an all-around robotics expert, but his specialty is perception. So Harsh, maybe you could tell us about the projects that students will build in this first term of the program.
Sure thing. In my opinion, projects are the best part of this program because this is where you get the most valuable experience of applying the knowledge you've got in the program. In the series of projects to come, you'll be building exciting applications to do things like autonomous navigation, mapping, manipulation of robotic arms, and control of drones following moving targets.
Awesome. Hey Brandon.
Howdy Ryan.
Brandon is the Chief Technology Officer here at Electric Movement. So we've just heard from Thomas and Harsh about what's going to happen in term 1 of the program. Maybe you could tell us what happens in term 2.
Sure. In term 2, you'll be learning about more advanced topics such as localization and motion planning. But what's more exciting is the fact that you'll be taking the artificial intelligence algorithms you've written and you'll be integrating them with a real robotics hardware platform.
Very cool. So you've got an awesome journey ahead of you, and we're all super excited to get started. So we'll see you in the classroom. The first project is styled after the NASA Sample Return Robot Competition. In a simulator, you'll use computer vision techniques to navigate and map the environment while searching for rock samples of interest. With this project, you'll quickly get a chance to experience the 3 essential elements of robotics: perception, decision-making, and action.
In the second project, you'll apply your knowledge of kinematics and ROS to manipulate a robotic arm with 6 degrees of freedom in simulation to pick up an object from one location and put it in another. This is a classic problem in robotics. and the solution is applicable across a wide range of industries, from agriculture to manufacturing and beyond.
In our daily lives, we often encounter a classic robotics problem: finding a specific object in a cluttered environment. If you're anything like me, the problem is twofold more difficult. In Project 3, you'll try to solve this problem for your robot. You'll take what you've learned about computer vision and use the PR2, an advanced two-arm mobile manipulator, to identify your object of interest, grab it, and then move it to a different location.
For the final project in Term 1, you'll train a deep neural network to identify and track a target in simulation. You'll then issue commands to a quadcopter to follow that target. So-called follow-me applications like this are key to many fields of robotics, and the very same techniques you apply here could be extended to scenarios like adaptive cruise control in autonomous vehicles or human-robot collaboration in industry.
In Term 2, you'll step out of the simulator and into the real world. You'll tackle motion planning, localization, and more using real hardware. This program is all about robotics. But before we jump right into it, I think we should back up a step and ask the question, what is a robot? So, Brandon, what is a robot?
Well, I'd say at its core, a robot is a machine that's responsible for performing some sort of task.
Okay, so a machine that performs a task. So, for example, my blender in my kitchen that performs the task of making me a smoothie. That's a machine that performs a task, a robot then?
Well, not quite. Maybe if your blender did all the shopping, bought all its own fruit, and then made you a drink. Maybe if there was some sort of autonomy.
That would be an awesome blender.
Yeah. It would also be a blender robot.
A blender robot. Okay, so I get it. So basically, it has to be autonomous. A robot is a machine that has no human operator.
Well, not really. So there are examples of robots that actually have human operators involved. For example, surgical robots like Da Vinci. These robots perform really difficult surgeries, but there's always a surgeon, a human behind the robot. The robot only aids the human to perform the surgery.
Right. I think to me, like, the perfect example of this kind of gray area between not a robot is actually a drone. So almost every drone now has the ability to maintain a constant elevation independent of any input from the human. So just kind of this altitude stabilization. A lot of drones actually have the ability to do a follow me mode. So it'll be able to lock onto a target and track them. So autonomous navigation and path planning. So it has modes where it can be just totally teleoperated, but it also has modes where it can be independently operating.
Okay, so there's like sort of a semi-autonomous requirement for a robot, but doesn't mean humans are necessarily totally out of the picture. You can have a robot that is somewhat controlled by a human and somewhat autonomous, but it's performing some physical task in the world.
Right.
Again, not really. So there are machines which don't perform direct physical tasks, and they're still considered robots. For example...
Well, what do you mean? No physical task, but it's still considered a robot.
Yeah, for example, Amazon's Alexa and Google Home. These devices perform the three basic operations just like a robot. They do sensing, they do decision taking, and then they perform actions. These actions are not necessarily directly physical actions. For example, if I'm ordering something using Alexa, the item is going to be shipped to my door, and I don't even have to go out.
Or you ask it a question and it comes back with a response.
Yeah, it gives you an answer.
No physical action.
So there's no physical actuation from Alexa's part, and it still performs all the three basic steps for the robot. So it's a robot.
In my opinion, a machine that cannot, perform gross physical motion to actually alter the physical world around it is not a robot. If it didn't, it's just a statue.
Not really.
Really.
What about robots that perhaps like a BattleBot? Would a BattleBot be considered a robot because it has the actuation component down? We call it a robot.
Well, in case of BattleBots, they don't have any sort of autonomy. And since they're completely controlled by their human overseer, I don't think they're considered robots.
Yeah, it would be a fancy exoskeleton, but a cool machine nonetheless.
Okay, so Amazon Alexa doesn't have the actuation, but it has everything else. It's a robot. But a BattleBot has the actuation and nothing else. And,
not a robot.
Not a robot.
Yeah.
Okay.
So what do you think, Brandon, is the most essential element of being a robot?
Well, I think in part it goes down to decision making and how decisions are actually made. So I can definitely say if it has actuators and if it has a component of artificial intelligence, then maybe it's a robot.
So artificial intelligence at the core of the decision-making process is something essential to robotics, or to being a robot.
Oh, yeah, I would agree to that.
What do you mean no? How is that possible?
Artificial intelligence, it is not a requirement. It just needs enough computational and decision-making resources to make independent decisions, to make intelligent choices, but it doesn't have to fall under this umbrella of artificial intelligence, machine learning, whatever the buzzword is of the day.
If it's taking intelligent choices, how is it not artificial intelligence?
So decision-making, we could say, is an essential element,
Essential,
but
yeah.
debatable whether it includes artificial intelligence or not.
I would go with that.
Okay, got it. So for the purposes of this course, I think we can all agree that there are 3 components that are essential. Basically, that a robot has sensors to perceive the world around it, that it has some capability to make a decision, and then that it takes action based on that decision or those decisions.
Yeah, sounds good.
I can
Cool.
look at that.
Robots perceive the world around them through the use of sensors. You can think of a robot's sensors as analogs to our human senses, like sight, hearing, and touch. There are many different kinds of sensors used in robotics. A robot's eyes might be cameras, LiDAR or radar units, or even ultrasound. A microphone could be a robot's ears. Giving a robot a sense of touch might be achieved through the use of temperature or pressure sensors. Even senses like taste and smell can be achieved using chemical analyzers. Robots can also be equipped with sensors that have no human analog, like GPS to establish exact positioning on Earth, a barometer to detect altitude, or even a magnetic field sensor to detect heading. In this program, you'll be getting experience with a wide range of sensor modalities and sensor data, starting with camera images in the first project.
Based on the data from various sensors and its own internal state, a robot needs to make decisions in order to accomplish any given task. These decisions can be as simple as answering a yes or no question, like is the target object present on the table? Or they can be extremely complex, like navigating an unknown environment. In practice, however, the decision-making process in robotics is complex and requires answering many questions to find a path through a complex tree of possibilities. Along the way, sophisticated techniques might be used, for example, to extract information from images or applying a Kalman filter to compensate for a measurement drift. A robot needs to use a motion planning algorithm to decide how to get from one place to another, and then use a control algorithm to stay on track. In this program, we'll be covering decision-making techniques all the way from simple decision trees to complex deep neural networks, so that you can give your robots the best brains possible.
While perception and decision-making are probably the most challenging pieces of robotics, the most exciting part is definitely action. Robots can take action in many ways and for many different purposes, like moving from one place to another, speeding up or slowing down, making a new sensor measurement, or even communicating with humans or other robots. Motors and actuators might turn wheels or propellers on a mobile robot or activate joints in a robotic arm. A robot might take other actions as well, like for example, power on a laser scanner to take a measurement, emit light or sound, or send a message in order to communicate. In this course, you'll get a chance to build robotic systems that take action, first in simulation and later using real hardware in Term 2.
This first project is designed to give you experience with all 3 of the essential elements of robotics: perception, decision-making, and action. The project is modeled after the NASA Sample Return Challenge, and your goal in this project is to program a rover to navigate autonomously in simulation and create a map of its environment while searching for rock samples of interest.
That's right. You'll accomplish this goal by first applying some basic computer vision techniques to images obtained from the forward-facing camera on the rover. You'll apply a color threshold and perform a perspective transform to identify traversable areas in your environment. After analyzing each frame, you'll update your map with newly detected obstacles and navigable terrain.
You'll apply a separate color threshold to identify the rock samples you're looking for. In the end, you will have created a map of the environment showing the extent of navigable terrain and the location of the samples you set out to find. Now we're going to show you exactly how to do that, so you can quickly get up and running to implement autonomous navigation and mapping.
For a successful submission of this project, you need to generate a map of the environment where traversable terrain, obstacles, and samples of interest are identified. If you're up for the extra challenge, we'll also be giving you lots of tips and tricks to complete the task of collecting those samples and returning them to the starting point.
Download the version of the simulator that's appropriate for your operating system using the links provided below in this lesson. Unzip the downloaded file and open up the RoverSim application. You'll get a startup screen where you can choose the resolution and graphics quality. Keep in mind that higher resolution and quality might cause your computer to run slow. You should also check the box next to Windowed so that the simulator doesn't take up the entire screen when you launch it. These settings will be saved for the next time you launch the simulator. Click play to get started. The home screen gives you the options to start in training or autonomous mode. Choose training mode for now. You can steer with the arrow keys or the mouse. If you're not moving, you will automatically turn in place using four-wheeled steering. This can help when you find yourself in a tight spot. In the lower left-hand corner, you can see the view from the camera on the front of the rover. If you hit the tab key, you'll shift between a view from the rover camera and one from the viewing camera behind the rover. If you hold down the right mouse button, you can change the perspective of the viewing camera and scroll to change the zoom on the viewing camera. So let's go for a drive. As I explore the environment, I see these interesting golden rocks here and there. These are the samples you wish to locate in this project. The rover is equipped with a robotic arm, and if you approach to within proximity of one of these samples, you can pick it up. You'll see the Is Near Objective flag in the upper left-hand corner has switched to Yes. At that point, you can use the left mouse button or the Enter key to activate the robot arm. So do some exploring yourself and collect some rock samples. To record data, launch the simulator in training mode and hit the R key. This will open up a dialog window where you can choose the folder you want to save data in. In that directory, the simulator will create a folder called IMG to save images and a file called robotlog.csv to record other data. I'll go ahead and save to the desktop. Keep in mind that if you've recorded data previously and there's already an IMG folder and a robotlog.csv in that location, they will be overwritten when you record again. So let's record some data. Now I can drive around, pick up samples, and do whatever I want until I want to stop recording, at which point I'll hit the R key again. At that point, you'll see the rover retrace the path you took while saving images and other data. Now, if you look in the IMG folder, you'll see a collection of images you've saved, and you can look at each one individually. In robotlog.csv, you'll see the path names to each of those images, and the data for steering, throttle, brake, speed, X and Y positions, as well as pitch, yaw, and roll angles. In the project, you'll use the recorded data and process the images to make a map.
Immediately after this video, you're going to see something that looks like this. And this is called a Jupyter Notebook. It is a great tool for writing and documenting Python code. So as you can see, this notebook is made of cells. And I've got a cell highlighted now, and I can use my arrow keys to navigate up and down through the cells. And this cell, as you can see here, is a markdown cell. And I don't want to talk too much about these, except to say that markdown is a sort of fancy way to make text look a little nicer. So sometimes you'll see these cells in this format, and this can be a little bit annoying. And if you don't know what to do, it can be a big problem. Basically, this format is showing you the editing mode. So here you can see the syntax for making something a header. And here you can see the syntax for making something bold. If you ever wind up in this mode and you want to get back to the nicer looking mode, so just like Control and Enter works in markdown cells, we can also look at a code cell, and here we have a Python comment followed by a print statement, and I can do Control and Enter here, and sure enough, it printed hello world. Now there's actually another way you can run a cell, and that's by pressing Shift and Enter. And that does the same thing, except it advances your cursor down to the cell below. That's actually really nice. So when you see a notebook like this one, and you start at the top, you can just kind of advance through by pressing Shift, Enter, Shift, Enter, Shift, Enter. And I'm going to let you play with this more on your own, but there are two important things I do want to say first. Number one, this is your workspace. You can do whatever you want in these notebooks. You will not cause any lasting damage. There's nothing to break. So, for example, I could go here and let's say I want to delete every single cell for some reason. I'm going to press the D key twice to delete a cell. And I'm going to do that on every single one. All right, so all my cells are gone. I could even save it. Now you may think we've caused lasting damage and we'll never be able to return to this exercise, but that is not true. Down here in the bottom, we select Menu and then go to Reset Data. And it looks ominous, but it's okay. We just type in Reset Data to confirm. The reason it's so hard to delete is because, this is your workspace. You may have a lot of work on here that you don't want to delete. So we just want to be sure that you don't do anything you don't want to do. But sure enough, after running Reset Data, we're back to where we started. So that's the first thing I wanted to say. You cannot cause lasting damage. And the second I want to say is that, again, this is really your workspace. You can even create new files. You can do whatever you want. So I'm going to create a new notebook in Python 3. Maybe I'll call it Math Practice. And I can play around with Python code. Let's try 2 plus 2. Sure enough, it's equal to 4. And I can browse all of my files by clicking on this Jupyter logo. Oh, it's prompting me to stay because I haven't saved my changes. That's good. Let me go through that process of saving the changes. Now I can click on the Jupyter logo again, and now I can see all of my files. Math Practice and Playground are both here. So I can click on Playground, and I'm back here. All right, I just wanted to show you those few things. You'll learn more as you play around in this programming playground, and you'll learn more about how to use this tool throughout the nano degree. Have fun.
Here we are again in the simulator. In the upcoming project, you'll apply a perspective transform to the camera images coming from the rover to shift them from the perspective seen from the rover's camera to one where you're looking down on the world from above. To do this, we'll use a reference grid that you can open up in the simulator by hitting the G key. Okay, so now we have a grid, and the way it's set up, each grid cell represents 1 square meter. If you zoom way out, you can get a feel for the scope of the map you'll be building in the project, where each pixel will correspond to 1 square meter on the ground. I've positioned the rover in front of one of these grid cells, so now I can see what the camera view looks like. To perform the perspective transform, you'll need to identify the 4 corners of a grid cell in the field of view of the camera. These 4 points will be your source points, or the points that define a square meter on the ground plane in the image. You'll then define the destination points, or in other words, the 4 points that will define that same square meter in a top-down view of the world. With your source and destination points defined, you're ready to use OpenCV to perform a perspective transform. This operation will transform your rover camera images from this perspective into a top-down, or map, perspective. Let's see how this works in practice in a Jupyter notebook. Here, I'm first going to invoke this matplotlib notebook command to allow me to investigate the images I'm plotting in the notebook. Next, I'll import OpenCV, NumPy, and some matplotlib packages to read in an image. So I've recorded some data and chosen this image as my calibration image, where I'm going to identify the pixel positions of the 4 corners of the grid cell in front of the rover. Let's have a look at it. Now I can move my cursor over this image, and at the bottom you'll see the pixel positions of the cursor as well as the RGB pixel values. This is how we're going to get the source points for the perspective transform. Record the values for X and Y of the pixel positions of each of the 4 corners of this grid cell. These 4 points define what a square meter on the ground looks like from the perspective of the rover camera. Next, we need to define where we want that same square meter to appear in our destination image. First, I'll define a function that uses the OpenCV functions getPerspectiveTransform and warpPerspective to do the heavy lifting. If you want to dig deeper into the math behind this method, check out the links in the lesson following this video. Essentially, we'll use getPerspectiveTransform to calculate the perspective transform matrix, M, and then apply that matrix using the warpPerspective function to generate a warped image. Here, I'm defining the source points as the pixel positions I found in the original image that marked the corners of the grid cell. I'm also defining the destination points, or where I want those source points to move in the final image. When I run this code, I get this result. Now, that original grid cell that appeared in front of the rover has been moved to here. And we now see it from a top-down perspective, so it appears as a square. Not only that, but all the other grid cells appear as squares as well. So we've succeeded in constructing a top-down or map view of the world.
If we look at our company right now, there are a handful of people focused on the business side, right? So the sales, the marketing, the legal, those aspects of it. We found a lot of people who have particular expertise, whether it's in technology or writing or as a nurse or as a lawyer, whatever it might be, but who have a passion for the problem that we're trying to solve, right? Which is helping chronic care patients get better care over time. And so what that means is if you look at the resumes or the backgrounds or the the LinkedIn profiles of people, it's a really diverse group, right? But if you look at what people are focused on, then it's a very cohesive group. I think that people with good, strong software backgrounds is more important than specifically what it is, right? So get good at anything, right? And then figure out where you want to apply that. With robotics as an industry taking off more and more, you see companies like ours and many others hiring more and more people with strong skill sets at the intersection of robotics and something else. Find what you are good at and what you enjoy doing and figure out how you apply that. Right. So I think what we see is, again, robotics in general is being applied in so many different industries. Obviously we're talking about healthcare here again and some of the things that that draws upon in terms of skill sets, but you can see an overlap with almost any skill set being brought to the table for interesting robotics applications now in industry.
One of the features of this program is going to be something that we call design reviews, which is a powerful way for students to learn how to communicate their ideas and justify them in the context of a group, which is something that's really important in industry and something that we've built the curriculum around. A design review is a comprehensive explanation and presentation on the problems you're trying to solve, your particular approach to solving those problems, and making sure that you're presenting those ideas to your peers in a way that communicates your ideas well and makes sure that you're working well with your team. At Electric Movement, we find design reviews to be especially important to our iterative design process. It's so important when you're developing complex systems to make sure you're getting good feedback. The great thing about a design review is it allows you to sit a bunch of different people with different specializations around a table and really look at a design and say, is this good enough? Does it properly consider its users? Does it really achieve its design goals as intended? The other thing we get to do in a design review is we get to ask ourselves, how well are we communicating? Could we have done that better? How fast and how good are we making decisions? And how much better can we be as engineers? A successful design review should answer the following question. What is the design being considered? Who are the users of this design? And what decisions need to be made over the course of this design review? An excellent design review should not just present information, it should present information in a way that solicits feedback in order to make important decisions.
Hi, I'm Kathleen. I lead the careers team at Udacity. We support students in their job search. The careers team knows what employers are looking for in a job candidate, and we want to work with you to market yourself as the best person for the job, whether it's a new role or a promotion at your current company. You need to be proactive in your career development to be job ready at graduation. For this reason, career services are available throughout your nanodegree experience. It's important to remember, while you're here to learn the technical skills for a job, it's equally important to know how to communicate those skills to an employer through an application, your online profiles, and in interviews. Let's meet the careers team who will be with you along the way.
Hi, I'm Rachel. Along with a network of career mentors, our team is here to help you from when you begin to look for jobs until you accept your job offer. Career support is present at different stages throughout your nanodegree, and we encourage you to go through all of them regardless of where you are in your job search. Udacity career services include guides, lessons, and personalized feedback on topics like talking to recruiters, interviewing, and optimizing your online profiles.
And I'm Trin. In order to graduate career ready, you should continuously work on your career development. Like with all learning, beginning something earlier means you're more prepared when it's time to apply that learning. When your dream job pops up, you want to be ready for it.
Hi, I'm Kirsten and I head up employer relations at Udacity. Once you've completed the career curriculum, you'll be ready to apply to jobs and talk with employers. Udacity partners with industry-leading companies who are looking to hire skilled and passionate people, like you. Having hiring partners means you'll have direct and preferential exposure at these companies. This will help give you a leg up in your job search as you explore your career options and develop a career path unique to you, your passion, your location, and other career goals.
After you complete your first core nanodegree projects, you'll then be prompted to begin your career development with us. We'll be there with you from then on as you explore your career options and pursue your dream role. We look forward to working with you.
Welcome to ROS Essentials. I'm here with Thomas and Brandon, who will be your guides through the next few lessons. So Brandon, what are these lessons all about?
These lessons are all about the Robot Operating System, or ROS for short. ROS is widely used across industry and academia for building robotics applications. After this quick introduction to the basic components of ROS, you'll have the tools you need to start building awesome robots yourself.
Fantastic. So Thomas, how does the content in these lessons relate to what students will be doing through the rest of the program?
We'll be using ROS throughout this program as our software framework to control super cool robots. In the lessons to come, you'll take what you've learned here and build on it to create some exciting projects.
Awesome. Well, let's get started then.
Hey Brandon, want to build a robot?
Sure, sounds good. Looks like you got some hardware here. What's left to do?
Yeah, all we need to do now is write device drivers for all our sensors and actuators, develop a communications framework that can support 4 different protocols, write algorithms to do perception, navigation, and motion planning.
Yeah, and then after that, we can implement a mechanism to log our data, write our control algorithms, oh, and don't forget error handling.
Awesome, let's get started.
So how's it going, guys?
Great.
Yeah, we got the lights to turn on.
Huh.
Building a robot used to be a long and cumbersome process. All the components had to essentially be built from scratch. In this lesson, we'll be giving you an introduction to Robot Operating System, or ROS, which is a software framework that greatly simplifies robot development. There are many advantages to developing robots with ROS, but before we dive deep, I think we should explain what ROS actually is.
Indeed. ROS is an open source software framework for robotics development. To help you get a better understanding of what ROS is, let's illustrate some of its components and features. ROS is not an operating system in the typical sense, but like an OS, it provides a means of talking to hardware without writing your own device drivers. It also provides a way for different processes to communicate with one another via message passing. Lastly, ROS features a slick build and package management system, allowing you to develop and deploy software with ease.
ROS also has tools for visualization, simulation, and analysis, as well as extensive community support and an interface to numerous powerful software libraries. Before diving deeper into all of this, let's take a brief tour of the history of ROS.
Development of ROS began in the mid-2000s as Project Switchyard in Stanford's Artificial Intelligence Laboratory. In 2007, ROS became a formal entity with support from Willow Garage. Since 2013, the Open Source Robotics Foundation has been maintaining and developing ROS.
One of the primary motivations for developing ROS was the recognition that researchers were constantly reinventing the wheel. There weren't many reusable robotics software components that could be used as a starting point for a project.
In addition, because different groups were all working on custom solutions, it was difficult for them to share code and ideas. It was also difficult to compare results. ROS aims to facilitate the development process by eliminating these problems.
So who uses ROS? Lots of people and lots of companies. There are drones, kinematic arms, wheeled robots, and even bipedal robots out there using ROS every day. Pretty much all of the robots we are interested in for this course share the same basic characteristics. They contain sensors for perceiving the world around them, software for making high-level decisions, and motors and controllers for actuation. ROS provides a powerful communication system allowing these different components to communicate with one another. Here, we'll introduce this communication system by considering a generic robot. This robot could be a drone, a mobile base, or even a robotic arm. While these robots may be composed of very different physical components, they are all built to perform these same 3 high-level steps of perception, decision-making, and actuation. On the software side, ROS manages these 3 complex steps by breaking each of them down into many small Unix processes called nodes. Typically, each node on a system is responsible for one small and relatively specific portion of the robot's overall functionality. For example, there may be nodes for each sensor and actuator in the system, as well as nodes for things like position estimation, behavior execution, and motor control. At the center of this collection of nodes is the ROS master, which acts as a sort of manager of all the nodes. The ROS master maintains a registry of all the active nodes on a system. It then allows each node to discover other nodes in the system and establish lines of communication with them. In addition to allowing nodes to locate one another and communicate, the ROS master also hosts what's called the parameter server. As its name suggests, the parameter server is typically used to store parameters and configuration values that are shared amongst the running nodes. For example, a mobile robot's wheel radius may be used by one node to estimate position and by another to calculate speed. Rather than storing the same information in multiple places, nodes can look up values as needed. Nodes can also share data with one another by passing messages over what are called topics. A topic is simply a named bus which you can think of as a pipe between nodes through which messages flow. In order to send a message on a topic, we say that a node must publish to it. Likewise, to receive a message on a topic, a node must subscribe to it. Here's an example of the topics, publishers, and subscribers for the nodes we introduced earlier. The arrows represent message flow from publishers to subscribers. It's important to note that each node may simultaneously publish and subscribe to a wide variety of topics. Taken together, this network of nodes connected by topics is called publish-subscribe, or a pub-sub architecture. Now that we've discussed topics, let's talk about the messages transmitted over them. Each ROS distribution comes with a wide variety of predefined message types which are available for your use. There are message types for communicating physical quantities such as positions, velocities, accelerations, rotations, and durations. There are also messages for communicating sensor readings such as laser scans, images, point clouds, inertial measurements, and more. The number of message types available in a full ROS install is actually quite staggering. Doing a simple search in my system, I was able to count over 200 different message types. However, even with so many useful message types available, there will still be times when you want to define your own. We'll tackle that later on in this lesson. It's important to note that although the name messages would seem to imply text-based contents, they can, in fact, contain any kind of data. Here's an example of the message types associated with the topics we looked at earlier. In this case, the topic called camera images is transporting image messages from the camera node to the position estimator node. The wheel encoder's topic is transporting rotation messages from the wheel encoder node to the position estimator node, and so on. Passing messages over topics between publishers and subscribers is useful, but it's not a one-size-fits-all communications solution. There are times when a request-response pattern is useful. For these types of interactions, ROS provides what are called services. Like topics, services allow the passing of messages between nodes. However, unlike topics, a service is not a bus, and there are no publishers or subscribers associated with them. Instead, nodes interacting via services do so on a one-to-one basis, using a request and response messages. Let's take a look at how a service might be used in the example we've been developing. Let's say that the behavior executor node wants to capture an image from the camera. We could just have it subscribe to the camera images topic. It would then receive a new image each time the camera node publishes one. However, this might be undesirable if the executor only wants to capture an image every once in a while. Instead of subscribing to the camera images topic here, we'll define a new service for the camera node. Let's call it capture image. The request message definition might be a custom message type called exposure time, and the response might just be an image message. By issuing a service call to the capture image service, the behavior executor node, or any other node for that matter, is able to request the camera should capture an image with a given exposure time setting. The camera node will then respond to the request by sending a message containing the resulting image. These diagrams of nodes and topics and how they're all connected are frequently referred to as compute graphs. Visualizing the compute graph is very useful for understanding what nodes exist and how they communicate with one another. ROS provides a tool called RQT graph for showing the compute graph of a system. A moderately complex robot will likely have dozens of nodes, even more topics, and quite a few services. This is EMBot, a mobile-based demonstration platform developed by Electric Movement. As far as robotics platforms go, this one is relatively simple, primarily consisting of a LiDAR unit, a depth camera, and 4 independently driven omnidirectional wheels. And here's EMBot's compute graph. It becomes clear pretty quickly why RQT graph is a handy tool to have around. It allows you to zoom in and pan around the graph, as well as choose exactly what information is displayed. Now that you've been introduced to some of the fundamental components of ROS's communication architecture, it's time to get some hands-on experience with a helpful little simulator called TurtleSim. Now that we have an understanding of some of the fundamental concepts of ROS, we can dive right into the command line where we will create cute little turtle robots with a package called TurtleSim.
Like this?
Yeah, just like this.
Okay, but hold on a second. We should probably stop and explain what cute little turtles have to do with robotics in the first place.
Indeed. Well, cuteness aside, the use of turtles in robotics goes way back to the 1940s.
That's right. Early roboticist William Gray Walter created some of the first autonomous devices, turtle robots, which he called Elmer and Elsie.
And in the 1960s at MIT, Seymour Papert used turtle robots in robotics education. Seymour's robots could perform a few basic functions. They could move forward or backwards by a given distance, rotate by a given angle, or they could drop the retractable pen on their bellies, allowing them to draw as they moved. These primitive functions could be triggered simultaneously, allowing the robots to move along complex trajectories and make sophisticated drawings.
This connection between robots and turtles continues to this very day. And in your first exercise with ROS, you'll be launching your own turtle robot in simulation.
In order to launch the TurtleSim package, you must first ensure that all of the ROS environment variables have been correctly set. Each ROS distribution provides a handy little script called setup.bash specifically for this purpose. The script is hidden away in the opt.ros kinetic directory, and you can run it with the bash command source. Among other things, the environment variables tell our bash shell where ROS commands and packages can be found. One simple way to determine if the environment variables have been set is to use the bash tab completion feature. Typing ROS followed by double tapping the tab key gives us an extensive list of all commands beginning with the characters ROS. There we go, there's our list. This list would be much shorter had we not sourced ROS's setup.bash. Later on in this module, we will become more familiar with some of the commands listed here. Having to source the ROS setup.bash script for each new terminal you open is quickly going to become painful. To combat the monotony, we can add the command to source setup.bash to our bashrc file. Bashrc is simply a shell script that is automatically run whenever you start a bash session. Now, when we open a new terminal and type ROS tab tab, we'll see the long list of ROS core commands. And there we go, there's our list. And that's it for setting up your environment. You're now ready to run the TurtleSim. Now that you've got your ROS environment variables in place, you're ready to run some TurtleSim nodes. So let's jump right into this. The first thing you're going to need to do is start the ROS master process. To do this, all you need to do is run the command roscore. And there we go. We've been hit with a wall of text ending with the line started core service. You don't need to worry about all the detail printed on the console, as none of it is really relevant to us right now. As long as you don't see any colorful red text disclaiming that there is an error, you're good to go. Now that the master process is running, you'll be able to run nodes. The first node that you're going to run is the TurtleSim node itself. To run the node, you'll want to open a new terminal and execute the ROS run command. The first parameter you'll be passing to the ROS run command is TurtleSim, the name of the ROS package containing the TurtleSim nodes. And TurtleSim underscore node, which is the name of the node executable residing in the package that you wish to run. And there you have it. You're running the simulator, and you've got a little turtle awaiting to be commanded around the window. To command the turtle to move, you must run another node, the turtle teleop node. Once again, you'll need to open another terminal window. And you'll run the same command you ran a moment ago with the exception of the node executable name. ROS run, TurtleSim, our package name, and turtle_teleop_key, the name of the node executable you wish to run. If you ever forget the name of the package or node that you wish to run, tab completion can be helpful. So let me go ahead and backspace. Let's say I don't know the node name, but I know that it starts with turtle. And then I hit tab. I see that the turtlesim package has two nodes that start with the word turtle. There's turtlesim_node, the node that we just ran, and then there's turtle_key, the node that we're trying to run. So rosrun turtlesim turtle_key. Okay, now the turtlesim_teleop node is running. With the turtle_teleop console selected, you can use the arrow keys to drive the turtle around the virtual world. Let's give this a try. Yep, and there we go. We're now ready to begin investigating the turtlesim comms. Now that you know how to start the ROS master and are able to run nodes, you can begin to investigate the topics and messages associated with the turtlesim node and the turtle_teleop key nodes. We'll be picking up the discussion from where we left off in the last screencast, which is to say ROS_core, turtlesim node, and the turtle_teleop key nodes are all running. Let's investigate exactly what's going on behind the scenes. If you had just stumbled upon this running system, you might be inclined to ask the question, which nodes are running? To answer this, you would open a new terminal and use the command rosnode_list. This command will query the ROS master for a list of all of the active nodes on the system and print them to the console. And there we have it, a list of 3 nodes running on the system. 2 of these nodes should look relatively familiar as we launched them explicitly just a moment ago. But what's the third? rosout is a node that's automatically launched by the ROS master. It's responsible for aggregating, filtering, and recording log messages to a text file. We'll learn more about that one later in upcoming projects, where we'll be getting hands-on experience with ROS log messages. In addition to getting a list of all active nodes, you will often desire a list of all topics. You can obtain the list of topics by using the command rostopiclist. This will give you a list of all the topics. We can see that there are some topics associated with the rosout node that we discussed a moment ago, and there are some topics grouped together under the turtle1 namespace. As you may have guessed, all of the topics grouped under the turtle1 namespace are provided by the turtlesim node and are associated with the turtle that we see in the virtual world. Publishing a message to the command_vel topic will command the turtle to move with the given velocity. Turtle1 also contains a color sensor, and the turtlesim node publishes readings from this sensor on the color sensor topic. Lastly, the turtlesim node publishes the position and orientation of the turtle to the post topic. While the topic names here are somewhat indicative of their purpose, this won't always be the case. Sometimes you will need to get more information about a specific topic. In the example here, even though you have a list of topics, some things are still relatively unclear. For example, the rostopiclist command does not tell us which nodes are publishing or subscribing to a topic, or what type of messages are being passed around. To get the information I just mentioned, you will use the command rostopicinfo. Let's start with getting information about the command_vel topic. rostopicinfo. And then the name of the topic you'd like more information about, in this case /turtle1/command_vel. And there you have it. The command_vel topic has one publisher, the teleop node, and one subscriber, the turtlesim node. This is actually as you might have suspected a while back when we were using the keyboard to command the turtle via the teleop node. The message type associated with the command_vel topic is a twist message, and it's part of the geometry messages package. You might be asking yourself right now, well, what is a twist message? To learn more, you'll use the rosmessage command. The rosmessageinfo command prints out message type information to the console. Let's get more information about the command_vel topic. First, I'm going to clear the terminal, and then I'm going to use the command rosmessage, show, and then the name of the package containing the message type. In this case, it's geometry_messages, as we saw a moment ago, /, and finally twist, the name of the message type. And there we have it, the full message definition for the twist type. You can see from the command output that the twist message is composed of 2 messages of type vector3, a type that is also defined in the geometry messages package. There's one 3-dimensional vector for linear velocity and one for angular velocity. Each vector consists of 3 different 64-bit floating point components, component x, y, and z. Float64 is one of the built-in primitive data types available to you when creating custom messages. To get more information about the built-in types and message definitions in general, check out the links in the text module accompanying this screencast. While rosmessageinfo is a very useful tool for getting information about messages, it does not tell us everything we may wish to know. Another tool at your disposal is rosed. rosed is a simple bash command that allows you to easily view and edit files in your ROS environment. Let's use it to view the twist message definition. Once again, I'm going to clear this terminal, and then I'm going to execute the command rosed, followed by geometry_messages, the name of the package containing the message in question, followed by twist.msg, the name of the message definition you wish to open. Note that if you've forgotten either the package name or the name of the message type, tab completion will come to the rescue. Alright, here we go. It's the actual message definition. It looks very similar to the output we saw from the ROS message info command, except there are a couple of important differences. The first thing you might notice is that there are no details about how each vector3 message is defined. This detail is elsewhere, particularly within the vector3.msg file also living within this package. The ROS message info command was simply doing us the favor of expanding the definitions in the console output. The second thing you might notice are the comments. This is the true reason that we came here. When in doubt, go to the source code. ROS message info didn't tell us anything about how the twist message is actually intended to be used, but the friendly ROS developer who created this message has our back. Most of the message type definitions that are part of the standard ROS distribution have a wealth of comments explaining how they are meant to be used. Here you can see that the twist messages are actually intended to contain linear and angular velocity vectors. This is something that might have been clear from the usage. After all, we saw that these messages were being passed around on the command vel topic. But it was not something that was clear from looking at the output of the ROS message show command. Once again, when in doubt, check the source code. This will be a common theme in ROS development. While viewing message definitions and topic information can be informative, sometimes the best way to understand what is going on is to look at the messages themselves as they are published to a topic. For example, when the turtle rotates left and right, which axis is it actually rotating about? And what are the units of rotation? Are rotations expressed in terms of radians or degrees? To get the answer to these questions, you can use the command rostopic_echo. Let's dive right into its usage. rostopic, echo, and then the name of the topic, /turtle1/command_vel. If you've forgotten the name of the topic, you can easily find it by using the command rostopiclist, which you were introduced to earlier in the screencast. When you hit enter, the terminal cursor will move to a new line, and it will appear as though nothing has happened. Fear not though, rostopic_echo is simply waiting for a message to be published on the command vel topic. In order to publish a message to the topic, we must jump all the way back to the console window for the turtle_teleop_key node. And I'm now going to hit the left arrow key. As expected, the turtle turned counterclockwise by some angle for about 1 second. I'd estimate that the actual number is somewhat maybe like greater than 90 degrees, but perhaps less than 135 degrees. Let's go back to the rostopic_echo terminal and see what happened. And as you can see, we've caught a message. All of the velocity components are 0, with the exception of the z component of the angular velocity. Here we see a value of 2. This tells us that when the turtle rotates counterclockwise, it is doing so around the z-axis. The magnitude of the velocity tells us that the units associated with the movement are probably in radians per second. How did I get there? Well, a quick math check will tell us that 2 radians corresponds to approximately 114.6 degrees. And there we have it. You should now have some understanding about rostopic_echo and how it can be used for investigating messages passing over a topic. As a side note, if this unit's investigation seems a little bit contrived, that's because it certainly was. Like any sensible engineers, the developers of ROS have elected to standardize around SI units wherever applicable, which is to say, length is measured in meters, mass is measured in kilograms, time is measured in seconds, and angles are measured in radians, and so on. You've now completed a brief tour of the ROS command line tools. Armed with this knowledge and the general understanding of the ROS communications architecture, you should be prepared to move on to the next step, setting up your first Catkin workspace. Great work! In this lesson, you've seen a high-level overview of the concepts behind ROS. You now know how the ROS master process functions as a parameter server and how it enables nodes to be connected over topics. Also, you've seen how ROS nodes communicate over these topics using message passing and services. This pub-sub architecture is a powerful and flexible design paradigm that will allow you to build a variety of robotics applications. Additionally, you've explored the TurtleSim package using ROS's powerful command line tools. These tools will be helpful to you as you build and debug ROS-based systems going forward, so be sure you are ready to use them in the upcoming lessons. Next, you'll learn how to build a basic ROS package called SimpleArm. For real-world robotics applications, you'll always start by creating a new development workspace and then adding software packages to it, which is exactly what we're going to do in the next lesson. ROS provides a powerful build and package management system called Catkin. Willow Garage, the early developers of ROS, named Catkin after the flowers on the willow trees surrounding their office. A Catkin workspace is essentially a directory where Catkin packages are built, modified, and installed. Typically, when you are developing a ROS-based robot or project, you will be working out of a single workspace. This singular workspace will hold a wide variety of Catkin packages. All ROS software components are organized into and distributed as Catkin packages. Similar to workspaces, Catkin packages are nothing more than directories containing a variety of resources, which, when considered together, constitute some sort of useful module. Catkin packages may contain source code for nodes, useful scripts, configuration files, and more. In the sections that follow, you will see how to create a Catkin workspace, add packages to it, manage inter-package dependencies, and lastly, how to successfully compile everything. One of the biggest benefits of using ROS is that it has a really large community of users and developers, so there's a lot of code that you can use. Let's clone an existing package and add it to our newly created workspace. You will start by navigating to the source directory. Then you will use Git to clone the simple ARM package for this lesson from its GitHub repo. Don't worry about trying to pause the video to copy the URL that I've shown here, as it's provided in the text module below. After the repo is finished cloning, you can change the directory to the top level of the ROS workspace and build the new package using the command catkinmake. I see an error. Could not find a package configuration file provided by Controller Manager. I happen to know that Controller Manager refers to a ROS package from ROS Control. We can fix this by installing the associated Debian package. If I didn't already know this, I would probably have to rely on a Google search to figure out the exact name of the package required. Okay, now that we have the Controller Manager package installed, let's try building again. I'm still in the top level directory, so I can just type catkinmake and hit enter. Awesome, so it looked like the build worked. Great, that wasn't so bad. Now we can run some of the code from this package that we just cloned. Up until this point, you've been launching nodes using the venerable ROS run command. As I mentioned previously, a ROS system usually consists of many running nodes. Running all of the nodes by hand, though, can be torturous. This is where the ROS launch command comes to save the day. ROS launch allows you to launch multiple nodes with one simple command, set default parameters on the param server, automatically respawn processes that have died, and more. To use ROS launch, you must first make sure that your workspace has been built and sourced. Recall, to build the workspace, you used the command catkinmake while you were in the root of the workspace. So let's move to the root of the workspace, and let's issue the build command catkinmake. Once the workspace has been built, you can source its setup script. The setup script lives in the newly created directory devel in the root of the workspace. In the same fashion as the setup.bash script in the opt-ROS directory, the workspace's setup.bash is responsible for setting up the environment variables which are responsible for letting the system find all of the packages, libraries, and other resources provided by your Catkin workspace. So let's go ahead and source that now. With your workspace sourced, you can now launch Simple ARM. To do so, use the command roslaunch, followed by the package name, for us Simple ARM, and then the name of the launch file, and here I'm just going to use tab completion, robotspawn.launch. Awesome, there we go, I've launched the ARM using the launch file and the Simple ARM package. A number of things just happened. Perhaps the most apparent is that I now have a robotic arm running in simulation. The simulator is called Gazebo. You'll continue to use it many times throughout this program. It is our surrogate for the real world. It's responsible for simulating forces and torques, the passage of time, as well as interactions between objects such as collisions. The robot I'm simulating here is a simple 2 degree of freedom robotic arm. It's perhaps hard to tell, but there's a little black ball on the end of the arm. The ball represents a camera. Gazebo can also simulate a wide variety of sensors. It's not just Gazebo that's running though. If you switch over to the console window and scroll up, you can see that ROS Launch has provided a brief summary of all of the nodes which have been launched and all of the parameters which have been set. I won't spend any time talking about all of the details of the launch file here, but I encourage you to check it out. It's in the launch directory within the Simple ARM package. Now that you understand how to create a workspace, add a package, build and launch everything, you're prepared for the next step, figuring out why the arm is just swinging around loosely in simulation. While I'll be explaining it thoroughly in the next section, I encourage you to try to figure it out before I spill the beans. Here's a hint. Check the log messages in the ROS Master console. I just launched my robotic arm for the first time, only to discover that it was swinging around loosely. I challenged you to figure out why, and I gave you a hint. Assuming that you're up for the challenge, you might have seen the following warning line. Controller spawner couldn't find the expected controller manager ROS interface. I'm going to jump right to the punchline here. It turns out that we are missing a runtime dependency. ROS packages have two different types of dependencies, build dependencies and run dependencies. You fix the first build dependency by using a combination of Google search and apt-get to install the ROS Kinetic Controller Manager package. Doing this allowed the package to build without complaints, but when you ran it, you got a warning, and things didn't function as expected. This is where the ROSDep tool comes in handy. The ROSDep tool will check for a package's missing dependencies, download them, and install them. Let's go ahead and take a look at the dependencies that were missing from the simple ARM package. Let's first go ahead and kill Gazebo and all of the running nodes. You can do so by entering Ctrl-C in the ROS Master console window. Now, in the root of your Catkin workspace with setup.bash source, you're going to want to type the command rosdep check. Rosdep, check, and then the name of your package. Here it's simple_arm, and then hit enter. And there you have it, a list of the system dependencies that are missing and where to get them. Now, we could have just used apt-get to install these, but I'm going to show you a trick. You can simply let rosdep do it. To make rosdep install packages, invoke the following command from the root of the Catkin workspace. Rosdep install -i space simple_arm, and then hit enter. The script will then install the missing Debian packages. And there you have it. Now, when you launch the SimpleArm package, everything should be operating as expected. The joint controller, now that it's actually on your system, will be loaded, and the arm will no longer swing around loosely. There we go. Gazebo has been launched, and as you can see, the arm is rigid. With all packages properly installed, you will now learn more about ROS packages in preparation for writing your own nodes in the next lesson. Congratulations! You now have some experience creating workspaces, working with packages and dependencies, and troubleshooting build errors. Additionally, you've had your first peek at Gazebo, a powerful tool for simulation that you'll be using over and over again throughout this curriculum. In the next lesson, you'll be writing additional ROS nodes for the SimpleArm package that you've already added to your Catkin workspace. Before you actually begin writing ROS nodes, make sure to take a peek at the links to the official ROS Wiki documentation surrounding the topics I've discussed here. The documentation is an extremely useful resource for ROS developers and will be very valuable to you throughout the rest of the program. Now that you've created a Catkin workspace and added the SimpleArm package to it, you're ready to write some ROS nodes. In this lesson, you'll be writing nodes in Python that publish and subscribe to topics, and you'll write a ROS service that can be called from other nodes or from the command line. The first node that you'll be writing is called SimpleMover. The SimpleMover node does nothing more than publish joint angle commands to SimpleArm. After you've developed a basic understanding of the general structure of a ROS node, you'll be writing another node called ArmMover. The ArmMover node provides a service called SafeMove, which allows the arm to be moved to any position within its workspace which has been deemed to be safe. The safe zone is bounded by minimum and maximum joint angles and is configurable via the ROS parameter server. The last node you'll write in this lesson is the lookaway node. This node subscribes to a topic where camera data is being published. When the camera detects an image with uniform color, meaning that it's looking at the sky, the node will call the SafeMove service to move the arm to a new position. With these new skills, you'll have everything you need to tackle the upcoming projects in this program. Here I'll step through the code for the SimpleMover node and explain what's happening at each step of the way. ROSPy is the official Python client library for ROS. It provides most of the fundamental functionality required for interfacing with ROS via Python. It has tools for creating nodes, interfacing with topics, services, parameters, and more. It will certainly be worth your time to check out the ROSPy API documentation in the links below. General information about ROSPy, including other tutorials, may be found on the ROS Wiki. First off, from the standard messages package, we import float64, which is one of the primitive message types in ROS. This package also contains all of the other primitive types. Later on in this script, we will be publishing a float64 message to the position command topics for each joint. At the top of the mover function, two publishers are declared, one for joint 1 commands and one for joint 2 commands. Here, the queue size parameter is used to determine the maximum number of messages that may be stored in the publisher before messages are dropped. More information about this parameter can be found in the links below. Here, I'm initializing a client node and registering it with the master. ArmMover is the name of the node, and the initNode function must be called before any other ROSPy package functions are called. On line 13, the rate object is created, and here we set it with a value of 10 Hz. Rates are used to limit the frequency at which certain loops spin in ROS. Choosing a rate which is too high may result in unnecessarily high CPU usage, while choosing a rate that's too low could result in high overall system latency. Choosing sensible values for all of the nodes in a ROS system is a bit of a fine art. Start time is used to determine how much time has elapsed. When using ROS with simulated time, as we're doing here, rospy.time.now will initially return 0, until the first message has been received on the clock topic. This is why start time is set and pulled continuously until a non-zero value is returned. Here we have the main loop. Due to the call to rate.sleep, the loop is traversed at approximately 10 Hz. Each trip through the body of the loop will result in 2 joint command messages being published. The joint angles are sampled from a sine wave with a period of 10 seconds, and in magnitude from negative pi/2 to positive pi/2. When the node receives the signal to shut down, either from the master or via SIGINT via the console window, the loop will be exited and the program will continue. Here, if the name variable is set to main, indicating that this script is being executed directly, the mover function will be called. The try except blocks here are significant as ROSPy uses exceptions extensively. The particular exception being caught here is the ROS interrupt exception. This exception is raised when the node has been signaled for shutdown. If there was perhaps some sort of cleanup needing to be done before the node shuts down, it would be done here. More information about ROSPy exceptions can be found in the links below. Assuming that your workspace has recently been built and its setup.bash has been sourced, you can launch SimpleArm as follows. Once the ROS master, gazebo, and all of our relevant nodes are up and running, we can finally launch the Simple Mover node. Alright, and here's what it should look like. Congratulations, you've now written your first ROS node. Here I'll step through the ARM mover code and explain what's going on. The imported modules for ARM mover are the same as simple ARM, with the exception of 2 new imports, namely the joint state message and the simple ARM service module. Joint state messages are published to the simple ARM/joint states topic and are used for monitoring the position of the ARM. The simple ARM package and the service module, SRV, are automatically generated by Catkin as part of the build process. The @goal function returns true if the joint positions are close to the goals. When taking measurements from sensors in the real world, there will always be some amount of noise. The same is true for joint positions reported by the gazebo simulator. If both positions are within 0.05 radians of the goal, true is returned. The clamp@boundaries function is responsible for enforcing the minimum and maximum joint angles for each joint. If the joint angles passed are outside of the operable range, they will be clamped to the nearest allowable value. The minimum and maximum joint angles are retrieved from the parameter server each time clamp@boundaries is called. The tilde here is the private namespace qualifier and indicates that the parameter which we wish to get is within the node's namespace. For example, here it's /simple_arm/. The second parameter is the default value to be returned. In the case that rospy.getParam was unable to get the parameter from the param server. The rest of this function simply clamps the joint angle if necessary. Warning messages are logged if the requested joint angles are out of bounds. The moveArm function commands the arm to move, returning the amount of time that elapsed while the arm was moving. Note: within the function we are using the rospy.waitForMessage call to receive joint state messages from the simple ARM joint states topic. This is a blocking function call, meaning that it will not return until a message has been received on the simple ARM/joint states topic. In general, you should not use waitForMessage. We simply use it here for the sake of clarity and because moveArm is being called from the handle_safe_move_request function, which demands that the response message is passed back as a return parameter. We'll talk more about this in a moment. This is the service handler function. When a service client sends a go-to-position request to the SafeMove service, this function is called. The function parameter REQ, or request, is of type goToPositionRequest. The service response is of type goToPositionResponse. This service function handler is called whenever a new service request is received. The response to the service request is returned from the function. Another note here. The moveArm function is blocking and will not return until the arm has finished its movement. Incoming messages cannot be processed, and no other useful work can be done in the Python script while the arm is performing its movement command. While this poses no real problem for this example, it is a practice that should generally be avoided. One great way to avoid blocking the thread of execution would be to use an action rather than a service. You can find some more information about when it's best to use a topic versus a service versus an action in the links below. Here, the node is initialized with the name ArmMover, and the goToPosition service is created with the name SafeMove. As mentioned previously, the tilde qualifier identifies that SafeMove is meant to belong to the node's private namespace. The resulting service name will be /arm_mover/safe_move. The third parameter to the rospy.service call is the function that should be called when a service request is received. Lastly, rospy.spin simply blocks until a shutdown request is received by the node. Failure to include this line would result in mover service returning and the script completing execution. Finally, we have the if name equals main block. This section of code is similar to that of SimpleMover. Okay, so let's go ahead and move through step by step and talk about the lookaway node. The imported modules are similar to those in SimpleArm, except this time we have the image message type being imported so that the camera data can be used. Here, we define a class for this node to better keep track of the robot arm's current movement state and position history. Just as in the node definitions before, the node is initialized using the rospy.initNode function. And at the end of the method, rospy.spin is used to block until a shutdown request is received by the node. The first subscriber, self.sub1, subscribes to the SimpleArm/joint_states topic. The node is written to check the camera only when the arm is not moving, and by subscribing to SimpleArm/joint_state, changes in the position of the arm can be tracked. The message type for this topic is joint state, and with each message, the message data is passed to the joint states callback function. The second subscriber, self.sub2, subscribes to the RGB camera/image raw topic. The message type here is image, and with each message, the lookaway callback function is called. A service proxy is how rospy enables calling a service from a node. The service proxy here is created using the name of the service you wish to call, along with the service class definition. In this case, armmover/safe_move, and goToPosition. The actual calls to the service will take place in the lookaway callback method. There are two helpers defined in the code, uniform_image and coord_equal. The uniform image method takes an image as input and checks if all color values in the image are the same as the color value as the first pixel. This essentially checks that all color values in the image are the same. The coord_equal method returns true if the coordinates coord1 and coord2 have equal components up to the specified tolerance. When self.sub1 receives a message on the SimpleArm/joint_states topic, the message is passed to the joint states callback in the variable data. The joint states callback uses the coord_equal helper function to check if the current joint states provided in data are the same as the previous joint states, which are stored in self.last_position. If the current and previous joint states are the same, up to the specified tolerance, then the arm has stopped moving, so the self.armMoving flag is set to false. If the current and previous joint states are different, then the arm is still moving. In this case, the method updates self.lastPosition with current position data and sets self.armMoving to true. The lookaway callback is receiving data from the RGB_camera/image_raw topic. The first line of this method verifies that the arm is not moving and also checks if the image is uniform. If the arm isn't moving and the image is uniform, then goToPositionRequest message is created and sent using the SafeMove service, moving both joint angles to 1.57. The method also logs a message warning you that the camera has detected a uniform image along with the elapsed time to return a nicer image. Congratulations! You've now come to the conclusion of ROS Essentials. Armed with the understanding of ROS you've learned here, you are now prepared for the projects to come.
While we've done our best to give you a solid understanding of the fundamental concepts of ROS, the lessons here are by no means comprehensive. Fortunately, there are a wealth of resources available online.
For example, there's the ROS Wiki. The ROS Wiki is the official source of documentation for all ROS packages. Additionally, there are many helpful tutorials there. Aside from a simple search on Google, this is probably the first place you should go if you're having ROS-related problems.
If the wiki doesn't provide the answers you're looking for, ROS Answers will be the next best bet. With tens of thousands of questions answered on ROS Answers, there's a good chance that somebody has already solved the problem that you're dealing with.
And there you have it. With these tools, you're ready to start building.
Welcome to our lesson on creating a professional GitHub profile. I'm Matt Leonard, a course developer at Udacity. In this lesson, you'll create or update your GitHub profile for use as a portfolio of your work. You'll also learn how to impress recruiters by contributing to open source projects. If you don't have experience with Git and GitHub, please take Udacity's course on version control with Git. Just follow the link in the instructor notes, then come back here when you're done, and we'll work on your profile. Artists use a portfolio to hold examples of their work. For instance, here's a couple paintings in my portfolio. I call this Octopus on a Swing, and this is 2 cellos and a baby. Similarly, my GitHub profile is a portfolio of my programming work. You can use GitHub the same way to show off your work to potential employers. Your profile will also show how you work. Don't worry, we'll go through various ways to make your GitHub profile into a professional portfolio.
Now, let's look at an excellent GitHub profile through the eyes of a recruiter. This is Scott Moss's profile. He's a software engineer here at Udacity. Over on the left is the personal information. A picture with a friendly smile can help recruiters make a connection with you, but it isn't mandatory. If you aren't using a picture of yourself, be sure to include a picture that somehow captures your personality, but nothing crude. Below is some general information and a link to Scott's Twitter account. Recruiters can look through Scott's tweets to get a sense of the things he's interested in. Similarly, I have a link to my personal blog. Also, make sure your username is something professional, like your name. It's not a good idea to name yourself after your favorite pop star. Okay, back to Scott's profile. Over here, we see a list of Scott's most popular repositories. These are ranked by the number of stars, which are given by other GitHub users that like the repository. The descriptions are nice so that we know what these repositories are for. To the right is a list of other repositories that Scott has contributed to. This is a clear indication that he is involved in collaborating with others on open source software. Employers can look through Scott's contributions to judge how well he works on a team. We can see that NGFX is really popular. We'll take a look at it later. Down here is the contribution chart. This is one of the first things a hiring manager is going to look at. Each square is a day. The darkness of the green indicates how many contributions were made on that day. You can see that Scott is very active, making at least one contribution most days. It's pretty clear that Scott spends a lot of time working with code, a good sign to a recruiter. Now we can check out one of Scott's repositories to get a sense of his work. Let's check out NGFX over here, the most popular repository he's worked on. We can see here that Scott made the most recent commit. If we click through to the contributors, it's clear that Scott has written most of the code. Going back to the repository, firstly we see a short description of the code. This is a library for making animations with Angular. He's also included a link to a GitHub page for the library. These GitHub pages are easy to create and very impressive. Here's the README, one of the most important parts of a repository. Its main purpose is to help others understand and use the code. A repository without a README has no starting point for someone to understand it. We'll come back to the README, it deserves special attention. Now we can scroll back up to look at the most recent commits Scott has made. Most of the recent commits are updating the version number and other chores, but there are some features and other additions too. We could look through some of these commits to understand how Scott writes code, but I'm not going to get into that now. Next, we'll hear from a hiring manager at Udacity about what he looks for in a GitHub profile.
I'm here with Art Gillespie, an engineer and hiring manager here at Udacity. Thanks for coming.
Oh, thanks for having me, Matt.
Of course. So what I asked you here for is that I'm trying to teach students how to use their GitHub profile as a portfolio to show off their work. So I want them to get a sense of what a hiring manager or a recruiter actually looks for from their GitHub profile.
Oh, okay, yeah.
So just start out, what is your role as a hiring manager?
Well, as a hiring manager, really, it's a collaborative role where I work with the engineers on the team and leadership, and we sort of figure out, what attributes do we value in engineers, and then we work closely with, we have amazing recruiters and HR people here. We work closely with them to sort of figure out how do we best screen for those attributes. And then, of course, I spend a lot of time actually, doing interviews, screening people, looking at people's GitHub repos, at their LinkedIn's and whatnot, and just trying to get a sense of the candidates and then making hiring decisions.
Cool. So when you're looking at a GitHub profile, what's the first thing you look at, and then why is it important?
Well, yeah, the first thing I look at is that sort of heat map at the bottom with the activity, the different shades of green, because that just gives me a really good sense of, does this person, are they passionate about coding? Yeah. And do they contribute often? And it doesn't have to be like all the time, but you see like sort of steady patterns. And I found that that just correlates with success in the workplace. People that love to code.
Awesome. And so when after your initial impressions, like looking at this activity chart, so what's the next thing you look at? Like, what else do you look at to get a sense of the candidate?
Well, for me, the next step is just to say, okay, well, here are the repos they've created, here are the repos they've contributed to, where have they done the meatiest work, and like pick one of those and just dig in. And I'll just spend, sometimes an hour just reading their code and trying to get a sense for the kind of, engineer they are. I'll also sometimes just dig into, have they contributed to other GitHub repos issues? How do they interact with other people in those discussions and whatnot? Are they a good collaborator? Are they patient? That sort of thing.
Welcome back. In the instructor's notes, you'll find a link to a GitHub profile. Imagine yourself as a recruiter looking at this profile. Identify parts that could be improved and mark them with the checkboxes. Now I'll go through the profile and give you my thoughts. The profile picture seems a little juvenile and you can't see the face clearly. It would be better to have a normal picture without a crazy filter. We also don't know what this user's real name is. Their username, acorn47, could be better, something based off the real name. There isn't any other personal information either. If I was a recruiter, I wouldn't know how to contact this person or anything about this person really. Descriptions of the repositories would be very useful here, so I can tell what kind of projects this person has worked on. And finally, we can look at the contribution chart. There's a bunch of commits here, then a couple commits later. This person appears to not have spent much time writing code. It's possible they made a lot of changes, but packed everything into one large commit. That's not a good sign. Now, let's go through a few quick fixes to spiff up your own profile. You can follow along as I fix mine. This guy here, if you don't know, is Andre the Giant, professional wrestler, actor, and all-around good dude. However, I'm going to need a better picture, preferably of myself, if I want to connect with recruiters. Also, I'm missing a bunch of other information like my name and where I'm located. GitHub has given me a prompt to flesh out my profile to help other GitHub users get to know me. Let's follow their advice. I can edit my profile by clicking through here. Here's where I can upload a new picture. Then I'll fill out my information, my name, the URL of my blog, my company, and finally my location. Now that I'm done with that, I can also change the names of my repositories if any need a better name. My repository names look fine. If I did want to change the name, I'd click the repository and then go to settings. Here's where you can change the name. Also, don't forget to comment your code. You'll probably end up showing off a couple sections of your code to an interviewer. Make sure it's commented and working. Go ahead and make any changes to your profile that you need to. I've provided a checklist that you can use to keep track of any improvements that you need to make. When you're done, mark this checkbox over here, and we can continue on to READMEs. A well-written README is one of the most important parts of a good repository. The README is necessary for others because it tells people what the code is for, how to build or install the code, and how to contribute. To teach you how to write a good README, I'm going to hand you off to my friend Walter.
Hey.
Oh, hey. Nice to see you.
For sure. Thanks for having me.
Thanks for coming. So I have some students who need to learn how to write READMEs.
Well, that's perfect because I teach a course on just that. It's less than an hour long, and it'll teach you everything you need to know about writing documentation for humans.
Thanks. So you'll find a link to Walter's lesson in the instructor notes. When you're finished with it, head back here and we'll continue. Hi, I'm back with Art. And now I'd like to get into commits and commit messages. So commits are one of the main reasons we use Git as a version control system. So you can make these incremental changes and you can see what changed every time you make a commit. And a very important part of this is the commit message. So why is the formatting of the commit message so important?
Well, I think a well-formatted commit message is, and probably the most important reason is git blame, right? Because as you go sort of digging through people's code or your own code, trying to figure out what's wrong, especially if you're looking for a bug. But sometimes you just want to know why a line of code is the way that it is.
Yeah.
The first thing you're going to do is run git blame. It's an awesome tool, and it's going to show you the committer, but also the commit message. And if that message is just like added stuff, it gives you no context for why the code changed or why it's there in the first place. And that's super important. It's super important for you as you maintain your code down the line. It's super important for people that follow after you and maintain your code. And so, yeah, it's funny. I definitely, when I look at candidates, when I dig through their GitHub, I check out to see, sort of how thorough and well they communicate in their commit messages. It's really important.
Hi again. Look through your recent commit messages and think about the formatting. How can you make the messages more clear and helpful? Think about how you would format them using the guide in the previous reading section. Just mark this checkbox when you're ready to move on. As a programmer, you are often going to be working with others on shared code, so employers want to see that you can collaborate. By contributing to open source projects, you can demonstrate how well you work with others. It also shows that you're helpful and love working with code. Hi, we're back. So I've been wondering how you know if somebody is a good collaborator, right? Because these candidates, when they get their job, and they have to work with other people on shared code bases. So how do you know from a GitHub profile if somebody's going to be a good collaborator?
So one thing I do to screen people for like how they'll work well on a team or how well they'll work on our team is to sort of branch out from the GitHub profile and maybe start with the issues on a repo that they've participated in and see how they participate in those threads and if they've commented on pull requests and whatnot, and just get a sense for how they interact with other engineers in the repo. Particularly, one thing that I think is really interesting is how whether they're patient with kind of people that may be newer to the community, and then from there, like I said, you branch out and maybe find if there's an internet relay chat channel that they may have been in related to a repo. And look at the logs and just see how they, are they helpful? Are they, are they kind? Or are they patient? And it's such an important signal because at the end of the day, you really want to hire people that are going to work well on a team, be a good fit for your team. And so yeah, I spend a lot of time doing that, just kind of digging in and seeing how they interact with other engineers publicly.
Yeah. So when you're talking about interacting with other engineers publicly, you mean on like open source projects, right? I know, personally, it's very daunting to start, working on this big library that all these other, really intelligent people are working on. So how would you start, or like what's your advice for, beginner, a new programmer to actually start contributing to these open source projects?
Yeah, it's a great point, Matt. I mean, it's really daunting, and I mean, even for me, and I know one thing that I do and that I recommend people do to just sort of, break the ice with a new project is like find some documentation, even the README. One thing I love to do is actually go through the README, clone the project, try to build it, try to get it running, following the steps in the README, and then try to clarify it based on the sort of problems that I had. Maybe it just needs to be updated a little bit. Submit a pull request with a few changes to the README. Those almost always get accepted. And it's just a great way to break the ice. I mean, you're going to move on to actually fixing bugs and then maybe actually contributing features. But just to sort of get into that community and get over that initial hump of feeling intimidated and there's just so much code and not knowing where to start, I find just contributing some documentation is a great way to start.
Cool. Let's go over how you can start contributing to open source projects. This is one of my favorite libraries, Pandas. Here we can see a list of issues that users have created. Contributing to the project can be as simple as helping a user with one of these issues. Of course, you can also create your own issues. These can be feature requests, bugs you've run into, or things in the documentation that you find unclear or incorrect. Be sure to be nice, this is all public. As Art said, one of the best ways to start contributing is by improving the documentation. Here's an issue related to the documentation. If you were working on this library, you could take on this issue, fix the documentation, and make a pull request. Finally, you can create a list of repositories you like by starring them. Also, if you watch a repository, you'll be notified of any changes. This is a great way to keep up with a library you're interested in working on. Welcome back. Go out and find an interesting repository you'd like to follow. For example, most of the popular programming languages have GitHub repositories, like Python and Node.js. Mark this checkbox here when you're done. As you are working on the rest of your nano degree, keep in mind that it's a good idea to contribute somehow to an open source project. If you don't know where to start, look through the documentation and fix a typo. Or if there is something in the documentation that isn't clear, create an issue about it and ask for help. Then you can rewrite that part and make a pull request.
Hello, I'm Mike Salem. I hope you're enjoying our Robotics Nano Degree program. Robotics is a huge field with lots of areas to study and discover. That's why we've put together some additional materials for you to discover called Udacity Explores. These materials are optional, but will give you insight into some of the areas of robotics. This extra content will be tied back into our robotics Slack community, where you can discuss and collaborate with our classmates from the community. The format for this material is simple. First, you will read research papers on active areas of robotic research. Next, you will see some of these areas in action and even hear from people working with these principles in the field. After that, you'll be given the opportunity to work with some hands-on experience, a few of these concepts, and collaborate with others. Once you're done, you'll be able to present your work to your peers and receive feedback on how to make your project even better. Finally, you will learn how to add these experiences to your resume to make you more marketable in the robotics industry, thanks to the help from our careers team. Please join me this week as we discover and discuss biologically inspired robots. We will journey through topics including why some robots are modeled after animals and how studying these animals may unlock future potential in the next generation of robotics.
Robotics has a lot to learn from biology. If you think about it, nature has been doing this job for hundreds of thousands or millions of years and has come up with these really intricate biological systems that are able to perform certain tasks really well. For instance, looking at the world and observing it through vision, or moving around using legs or wings or other forms of locomotion. These are all ideas that we can always use in robots and apply them when we're trying to solve physical problems. Biologically inspired robots are used in a lot of different applications. For instance, for carrying heavy loads, for search and rescue and surveillance and reconnaissance, and just in general exploration of areas that are too hostile for humans. And they're modeled after animals or sometimes humans, depending on the particular application. For instance, if you want to make a resilient robot that is able to travel across all sorts of different kinds of terrain, wheels might get stuck or might have other problems. So sometimes a six-legged insect-like robot is much more efficient. And it's not just the six legs that we're borrowing in terms of inspiration. We also model the movement of the robot based on insect gait, how the different legs move in coordination with each other. When you look at insects and birds and how they fly, that's a very interesting sort of dynamic that they have, which is completely different from all the planes and helicopters that humans have come up with. And in some scenarios, that sort of wing movement is necessary in order to be able to fit into smaller packages or smaller areas. So that's another place where we use biological inspiration. One of the areas in which bio-inspired robots are being deployed successfully are nanorobotics, where we're basically modeling these robots based on tiny microorganisms. And that works really well because microorganisms are really good at surviving in human bloodstream and in different cavities in the human body. And if you model your robot based on that, you're not only able to tap into, hundreds or thousands of years of evolution that has created these microorganisms, but you're also able to function in a similar way that these microorganisms function and get to the different parts of the human body that you might need to in order to treat them or to deliver certain medications. And in general, when you think of human environments and you want
robots to be able to participate in those environments and work with humans. Sometimes you want robots that are more human-like or humanoid robots. And that's one area which the recent DARPA Grand Challenge explored to a lot of detail by posing some tasks, like human-level tasks, and asking robots to perform them. So biologically inspired design works into robotics in a few different ways. The way I like to approach it is to think of the environment around us as humans. We have designed it to be suitable for us, right? And now if you introduce robots into the equation, they need to be able to adapt to the environment just like we do, right? So a simple example is we have stairs in our homes, right? Not all robots, especially wheeled robots, will be able to go upstairs. Then it makes sense to build robots that can adapt to an environment like that. So that means maybe robots with legs, or maybe robots that can fly. So that's one reason for looking at nature or biology for inspiration. The other thing is that nature has had millions of years of evolution to perfect things and get things right. So a lot of systems have evolved in biology that solve these real-world hard problems really, really well. So it only makes sense to get some of those ideas and involve them in making robotic systems. Animals are really good at locomotion in terms of moving around over the terrain, hunting, and even sort of facing calamities and emergencies. So consider cockroaches, for instance. Why are they so resilient to sort of being extinguished? Is because they have fail-safe systems. They have like multiple legs, and even if they lose one of them or one of them gets damaged, they can still keep moving around. Similarly, like cheetahs can run over open terrain very fast, and even if there is a little bit of disturbance in the terrain, they can overcome it. So they have a lot of these systems built in, a combination of skeletal systems, muscles, and just sheer wiring of things that makes them really resilient and robust to natural environments. There are some other examples which are kind of, again, more edge cases, including underwater robots that can float through pipes and sewer systems in order to find faults. There are some other sort of systems being designed for medical applications that are built on microorganisms that sometimes have like small feelers on the sides in order to sense, where they're going and whether they've attached to the correct place or not. So there's a vast range of animals that we've drawn inspiration from. Actuators are basically any component that enables the robot to move or perform an action. Roboticists, when they think about actuation, they try to measure how much energy they can get out of a certain unit mass of components, right? And right now, most of our traditional sort of actuators, including motors and linear actuators, are not really as energy efficient as biological systems. So these days, people are trying to come up with, non-traditional materials like piezoelectric materials, which will change shape or contract when electricity is passed through them, so they behave just like muscles. And you can both get higher energy density, but also different kinds of motion by applying these concepts. Batteries are a big concern in robotics because they are the primary source of energy for the robot, but they're also dead weight in some sense. If you look at biological systems, they have a much better distribution of where they store energy and where they use energy. And we're only beginning to explore some of these ideas of how to better spread around energy throughout a robot's body. Other things that researchers are looking at are alternative forms of energy. So for instance, in underwater robotics, you can imagine that if we are able to harvest tidal waves or tidal energy, that'll be a freely available and ubiquitous form of energy for underwater robots. So that's something that people are looking at. So you have to keep in mind that robots can be of different types, and in certain categories you don't really need to be worried about battery sources. For instance, if you're working in a machine shop or warehouse, then you might actually be plugged in or have a charging station nearby. But there's this whole other category of mainly autonomous robots that are exploring, for instance, interplanetary systems, or just robots out in the wild that do need to have an energy source and do need to be smart about how they use that energy. There are lots of aerial robots, including quadcopters, which are now being called drones, and then flying insects that are really, really cool. We're slowly getting to the point where the power source can be built in on board, but most of these systems currently work off a tethered connection that provides them with power. Grasping and manipulation are really hard problems in robotics because you don't really think about how much complexity is involved in carrying out those actions. Biological systems sometimes solve this problem using different approaches. Instead of completely, modeling the motion of a grasping arm and fingers and how they work to grab something, sometimes we have much more coordinated pieces that just move together in order to carry out a grasping action. Humans, for instance, human hands have haptic feedback, which plays a very, very important role in figuring out how much pressure you need to apply in order to grab something. And that's sort of built into our sensory system. So similar ideas are being used by roboticists to build arms that are much more flexible at grabbing different kinds of materials. Everything from delicate eggs to mugs to harder and heavier objects. Humans have an additional signal that they can process while they're performing activities like grasping. So if you think of the gravity all around us, it's pulling things down. So we have this notion that's built into our sensory systems that always uses that piece of information. So when you grab something, you can sense that it's slowly slipping down your hand, and you use that as a signal for how hard you need to grasp something, and that force is called shear. In general, for bio-inspired robotics, I think there are a lot of challenges in terms of figuring out how to store the energy needed to power these different biologically inspired components, how to coordinate things better. Because if you think of biological systems, we basically have a neural mechanism where impulses are traveling between neurons and they're activating different things, and they have a natural arbitration mechanism. Like when you feel yourself sort of fighting something, for instance, you really want to do something, but then you also realize that it's not the right thing to do, and there's a conflict between those two lines of thought, you can actually sense that in terms of a tension that builds up in your muscles. And that's the sort of natural form of arbitrating between different signals. Now we need to build similar mechanisms in robotic systems to fully utilize this idea of combining different behaviors. So you have to be very careful when you think of using biological inspiration in robotics, because not all problems can be solved by robots in the same way as biological systems do. One of the reasons is that the hardware that animals have or humans have is completely different from the hardware that robotic systems have to be designed with, right? We can't really build robots out of bone and flesh and muscles. So a lot of our design choices in terms of what pieces of hardware we pick, how they function together, are kind of constrained by the materials we can use. When we think of biological inspiration, we should think of that in abstract, like what are the overall properties of biological systems that make them more successful, and how do we replicate those same behaviors using artificial systems. I actually visited the MIT Museum recently, and that has a really nice collection of robots from different generations, robots of all sorts of different sizes, shapes, and things that they do. Starting from a one-legged robot, basically a pogo stick that tries to balance itself, to two-legged robots that are like a human that has been chopped off at the waist. That's what they look like. To four-legged robots, including the Boston Dynamics Big Dog, but there were some other models. And they look really clunky and mechanical to start with, but when you actually see them moving, they're even scarier, because it's this big hunk of metal sort of trying to move around. So I think I was most impressed when I saw Boston Dynamics Big Dog when it came out, because it has the right level of being inspired by biological systems, but also at the same time very practical and efficient at what it does. So it's basically a big dog that carries a lot of heavy load for mainly designed for military infantry. While they're going into battle, it can carry all their load behind them. So computer vision is a critical part of most robotic systems, especially those that are trying to act in a similar physical environment as humans, right? So if you think of one category of robots are those that are behaving or working on very specific tasks within a highly controlled environment, like assembly line robots, etc. And they typically don't need the same kind of perceptual variety as other robots do. So on the other hand, if you think of robots out in the wild or in very complex situations, like in the recent DARPA Grand Challenge, they need to be able to process a lot of different things that are going on, and they need to be able to do that in a smart way so that they don't, they're still performing their tasks on time, and they're able to, make up for any unexpected scenarios that come up. So now, how do robots do that? If you think about how humans and other biological systems do it, then you might get some ideas, right? Having two eyes enables us to do more than just observe static images. It enables us to, for instance, perceive depth through stereo vision. It also helps us in focusing our eyes and making sure that we can see clearly the thing that we're trying to attend to. So these are some ways in which we can use ideas from biological systems in order to better design vision systems for robots. Another example is optic flow, which is basically when we're walking or moving, or when some other object is moving with respect to us, we're able to gauge how fast it is moving or what direction it is moving in by looking and studying the patterns of the image changing, right? And this is again a concept that comes from early psychological models of human perception. So we've been able to take a lot of these learnings from psychology and neuroscience and then build them into robotic systems. Another very interesting topic is that of foveal vision. Now, if you think about it, our eyes are built in such a way that the density of photoreceptors is really high in the center of our visual field, and then it tapers off as you go outside. Now, you might think that's a waste of space. Like, why don't we have more photoreceptors just everywhere in like a uniform distribution? Now, it's actually, if you think about it properly, it's an information processing problem. If you have a lot of photoreceptors, there's a lot of resolution, and you would end up having to process images at a very high resolution all the time. But you don't always need to do that. You can process your overall visual field at a lower resolution and just process the center of your visual field, the thing that you want to focus on, at a higher resolution. And that's essentially what our biological systems accomplish. It's something that we haven't fully adopted in robotic systems, but there are some projects that have tried to combine like one wide-angle low-resolution camera and a very narrow-angle zoomed-in high-resolution camera and track together in order to achieve foveal vision. I think cameras have sort of developed in a completely independent sort of track, mainly to record images and then reproduce them at a certain level of quality. But if you think of the problem of sort of keeping things in focus or keeping your eyes on a certain object, those are the same problems that we face in vision systems. So we can sometimes look at alternate industries in order to also sort of adapt some ideas from there. So human eyes are not structured like camera sensors in any way, right? So camera sensors have this rectangular arrangement of pixels, and that's the form in which images come out of. But human eyes are much more complex. They have a higher density of sampling in the middle and lower on the outside. That's the foveal vision part. But also they're not organized in a rectangular grid. They're organized in a more radial grid. So a more appropriate sort of coordinate system, if you will, for an eye image would be a polar coordinate system. And sometimes that has a lot of advantages. Like, when you're moving around in the world, it's probably more natural to analyze images in the polar coordinate system because the positions of objects will change differently based on what coordinate system you're using. For instance, something that is coming towards you will basically increase in size, and its extents will basically increase the radius that it subtends on your visual angle. Whereas if you analyze that same thing in a rectangular system, then it will have a different kind of effect on the image being formed. So in some sense, if we make further progress into adopting biological vision systems for robots, a polar coordinate system might be something that enables us to do better kinds of analysis. So bees, for instance, the reason they use ultraviolet spectrum is because certain flowers give out light in that spectrum that then attracts them, and then they can find nectar in those flowers, right? So you can imagine that biological vision systems are tuned for these specific applications. Now, if we use the same idea here in robotics, for instance, for search and rescue robots, which are looking for humans in trapped places or in the middle of debris, then it's very useful to have some signal that can easily distinguish a human body from the rest of the surroundings. And one possibility is to use thermal imaging or infrared. So that's one way where we can adopt the same kind of ideas that are being used by animals in robotic vision systems. But in general, what you have to keep in mind is computer vision is not just about processing, information in the visual wavelengths, but in general, it's about processing information of the same type. So it could be visual data, it could be infrared data or ultraviolet data, or it could even be LiDAR sensing data. So if you think of how these biological systems have survived for hundreds or thousands of years, it's because a lot of robustness is built into these systems. For instance, processing of information is distributed throughout our different biological systems. In terms of vision, some processing occurs at the retinal level where very low level color differentiation, etc. happens there. But then higher level processing, for instance, recognizing faces or motion, happens in the layers of the brain. So there are very interesting edge cases that come out as a result. For instance, if your eyes fail you, sometimes your brain can still make up for that by filling in gaps, right? By inferring things from the surrounding context. Sometimes when certain layers of your brain are damaged, then you might have weird sort of results, things that are like gaps in your perception that result even if you have a functioning eye. But in general, what we can learn from these sort of examples is that when we design robotic systems, we should build in these points of resilience throughout the pipeline. Artificial vision systems are really well designed for certain kinds of applications, like analyzing something that's moving by or passing by, or for instance, counting people that are traveling through a mall or through an enclosed space. It becomes really hard when you throw sort of unconstrained problems at them, like putting a camera on a robot that's trying to move around in complex environments. And in these cases, it does help to have an attentional mechanism built into the robot. That helps simplify problems down a lot. For instance, when you and I are walking through a room, we'll fixate on a certain object for a fraction of a second or sometimes for a few seconds and look at that. That actually serves as an anchor for our eyes, and our vestibulo-ocular muscles try to keep that object at the center of our vision. That helps us move around in the world without getting disoriented. Because otherwise, imagine if your eyes were just stuck in a certain sort of relative position to your body, and your body sort of ambling about, your entire vision field would shake and move around, and it'll be very difficult for your brain to then process those signals. So a combination of attention and then the movements that take your eyes from one point to another, called saccades, and fixations, which is basically fixating on a single object, that combination of mechanisms enable us to process information more efficiently. Control systems form the mapping between perception and action. So if you want to design a control system for a particular robot, you You start having to think about what are the possible set of actions that the robot or the system needs to carry out. What is the complexity of those actions? For instance, if it's a wheeled robot and it only needs to move around like, forward, backward, and turn left and right, that's basically 2 dimensions of motion, right? But if you have an arm with multiple joints and then a gripper, that's that many dimensions of motion and that much more complex. So that's one source of complexity for the control system to handle. Another source of complexity is the input that is coming in. So again, if you think of a simpler robot which has simple distance sensors in the front and back and maybe on the sides, maybe there are 4 total sensors, that's 4 sources of input, that's it. But if you have a camera, for instance, that camera has a certain resolution and it's that many pixels worth of information that's coming in every frame that you have to process. That's another source of complexity. Now, how do you go about taking this one source of complexity, another source of complexity, building an efficient control system around that? And especially when you might have to design multiple behaviors within that system. So one of the approaches is called behavior-based robotics, where you break down the overall functioning of the robot into simple behaviors and then develop them almost independently, and then build in a mechanism to combine their performance. So let me give you an example. Think of a robot that is meant to explore an environment but then not bump into things, right? So you can think of its most critical behavior is to avoid obstacles. And let's say that is built in as the lowest layer of that behavior-based robot, right? In the middle layer, we can think of it sort of wandering around. That wandering around can be coded in as a simple behavior independent of the obstacle avoidance behavior. And then maybe at the topmost layer, we build in a mechanism for the robot to keep an eye on what spaces it has already explored, and then encourage more exploration by going to places it hasn't been yet. That's again another independent layer of behavior. Now, how do you combine these behaviors? Well, one simple idea is to basically say that as long as the obstacle avoidance behavior says we're okay to go, let's keep moving using 2 and 3, right? Whenever there is an obstacle that comes up in front of us, then the obstacle avoidance layer basically says, hey, stop. Like, let's rethink this and let's try to find a different place to go, a different direction to wander in. And that's one way of combining things. There are other more complicated ways of combining these behaviors that actually result in very complex behavior coming out, but it's all composed from these simple behaviors. And that's the subject of the subsumption architecture that Rodney Brooks and all had come up with and had become really popular for a certain period of time in robotics. Now, it is very challenging to develop these behaviors independently, but then also to combine them into one coherent system. Now, there are some advantages to taking this approach. One is that you can build these behaviors and optimize and tweak them independent of the others. So you could train the robot to be really good at avoiding obstacles, or you can train the robot to be really good at exploring spaces and do these without complicating them with these other possibilities that might come up, and then later worry about how to combine those activities. And if you think about it, this is something that biological systems do really well. For instance, if I'm walking from point A to point B, and somebody spills a glass of water in front of me, then I automatically come to a stop. I don't really consciously think about stopping. It's just these two behaviors have a sort of interplay that results in me stopping whenever there is an emergency that occurs, but it allows me to keep moving when everything is normal. It's amazing how babies learn the different activities and actions that they do and then grow up to be more coordinated human beings like you and me. And the way they do it is by a process of exploration and exploitation. And some of those ideas have been absorbed by the machine learning community in the form of reinforcement learning, where instead of explicitly training and optimizing the parameters for different kinds of actions and movements, we basically jointly optimize all these different parameters based on the end result or the end task that we're trying to accomplish. For instance, it's really hard to train a robot to play table tennis, ping pong, right? Because most of these robots are built with very articulated joints and arms that move in a very high dimensional space. And so how do you train them to play table tennis? Well, you have a reward function in mind. The reward function is basically whether the robot is able to hit the ping pong ball or not. And you use that as a feedback signal to tell the robot, oh, you did well, or you did not do well. And then over time, it slowly learns how to coordinate its movements in order to play well. And a similar kind of technique can be used to, for instance, train walking robots or humanoid robots or maybe quadruped robots. How do you come up with that whole control system that learns to coordinate the different legs so they fall just at the right time to prevent the thing from falling over, right? Instead of going in and trying to explicitly program all those movements, you can basically let a reinforcement learning or an evolutionary learning algorithm experiment with different kinds of motion in simulation and then come up with the best policy that makes it move most efficiently. So a lot of progress has been made in the field of reinforcement learning that tries to basically take an algorithm that works in one context and tries to apply that to a completely different context. Because if you think about it, what reinforcement learning does is it's learning how to map a set of inputs and state information to the appropriate action to take. And you can imagine that some of those algorithms that perform that learning can be used across different domains. So one of the most interesting domains that I've seen reinforcement learning being used in is the control of autonomous helicopters. And the way they did it, I think it was a Stanford project. They took a helicopter and then had humans fly it in different really crazy ways, performing different kinds of aerial maneuvers, loops and flips and everything. And basically trained an artificial system to then replicate those same movements. And they used a combination of physical movement along with simulation in order for the system to then try out different sort of motions till it got the controls perfect. And then they actually tested it on the real life helicopter, and it could perform those crazy maneuvers, sometimes with even more precision than humans. So reinforcement learning, or any sort of learning algorithms, work on a principle of trial and error. So they need to perform certain activities and then see how well they're doing and then improve their own parameters based on that. Now, when you start a learning algorithm, it typically performs very badly. And if you think of putting that sort of learning algorithm on a physical system, what that basically translates to is a robot that is making random erratic movements. And that can sometimes be costly and dangerous, right? We don't want to let these robots just run around in the wild, whacking things till they figure out how they can move the way they're supposed to. So what you do is basically run simulations where the movements and the physics are replicated as well as we can, and then once we have a control system developed to the extent that we are confident about it, then we try and deploy it on a physical system. But one thing that people don't really think about is that simulations are also used by humans and other animals to improve their own behavior. So if you think about it, when you sort of experience something for the first time and then go back and reflect upon it, you're actually running simulations in your mind, exploring the different possibilities that could happen or could have happened and how you would have reacted in those situations. It is this way that humans are able to learn with such a small number of examples. Sometimes you only need to be shown something once and you're able to learn from it. That's because at the back of your head, you're always playing these scenarios out. And we're kind of doing the same thing with simulations in robotics.
Now that you have the tools you need to start building robotic software systems, it's time to start applying those tools. So Harsh, where are we ultimately going with this next series of lessons?
Well, in this next project, you'll be operating a sophisticated robotic arm or serial manipulator in the simulation. In this case, you'll actually be operating the KUKA KR210, a robotic arm that is widely used in various industrial applications. In the project, you'll program the KUKA arm to complete the task of picking up an object from one location and putting it down in another.
That's right. But before you do that, you're going to need to brush up on some theory. So to begin, we'll take a step back from ROS and Gazebo and all the fun tools you got to play with in the previous lessons and plunge deep into the math of kinematics. You'll learn how to solve what's known as the inverse kinematics problem, which will allow you to command any serial manipulator along a pre-planned trajectory toward its target.
After you got the math down, we'll jump back into ROS and Gazebo to get your environment all set up for the project. You'll see how to apply your knowledge of kinematics to the specific case of operating the KUKA arm.
Sounds like a plan. This is a super fun project, and the skills and techniques you'll learn in these next few lessons are extremely relevant across a wide range of applications in the robotics industry.
Kinematics is a branch of classical mechanics that studies how things move without considering the forces required to produce the motion. And it's a subject area that is fundamental not only to robotics, but also to many areas of engineering. More generally, kinematics is used to help answer all sorts of interesting questions, like how to optimize human movements, design complex machines, or even predict the motion of celestial bodies. The project at the end of this lesson requires you to solve a common task for a robotic arm, picking up an object and placing it somewhere else. But to be successful, you'll first need to learn several important concepts, including reference frames, generalized coordinates, degrees of freedom, and homogeneous transforms. Reference frames are fundamental to kinematics. Vectors such as position, velocity, and acceleration are always described in the context of a reference frame. Most robots, such as the serial manipulator you'll be working with in the upcoming projects, have multiple degrees of freedom, which means that to understand the configuration of the robot at any given time, you need to know things like the angles and positions of various components of the robot simultaneously. Using multiple reference frames to describe the configuration of your robot can greatly simplify the analysis because vectors can always be described in the most convenient frame. But multiple reference frames create a challenge. How can we relate vectors expressed in one frame to those expressed in another? The answer to this question is the homogeneous transform, which is a 4x4 matrix that captures the relative rotation and translation between two frames. In this lesson, you'll see how to chain multiple homogeneous transforms together so that, for example, you could describe the position and orientation of the robot's end effector to that of the base. By creating these mathematical expressions that describe the relationship between each of the reference frames in a system, you'll have the tools to solve the two basic kinematic problems associated with serial manipulators, known as the forward and inverse kinematics problems. In forward kinematics, the joint variables are known, and the goal is to calculate the position of the end effector in Cartesian coordinates relative to the base frame. The aptly named inverse kinematics problem is the opposite scenario. Here, the pose, or position and orientation, of the end effector is known, and the joint angles that would achieve this pose must be calculated. As you will see, solving the inverse kinematics problem is much more challenging than the forward kinematics. Most serial manipulators used in industry have between 4 and 6 degrees of freedom. Denoting the fixed base as link number 0 and the first movable link as link number 1, then links number 1, 2, and 3 are usually referred to the arm. Any other jointed segments after the arm make up the wrist. Quite often the wrist is composed of 3 revolutes whose axes of rotation all intersect at a common point. This type of wrist is known as the spherical wrist because it provides 3 rotational degrees of freedom, just like a spherical joint. The toy robot arm I have here has a spherical wrist. If you look closely, you can see that the end effector rotates about this axis. The next link rotates about this axis. And finally, the boom rotates about its own longitudinal axis. All 3 axes of rotation intersect at a single point here. As we'll see in future lessons, a spherical wrist has many nice properties in terms of the Jacobian, inverse kinematics, and motion planning. These properties are due to the fact that the first 3 joints control the location of the wrist center, while the last 3 only control the orientation of the end effector. One of the ways in which manipulators are classified is in terms of their kinematic configuration of their arm, that is, the sequence of joint types for the first 3 movable links. With only revolute and prismatic joints, there are 8 possible permutations of arm types. However, only 4 types are commonly used in industry. These are known as Cartesian, cylindrical, anthropomorphic, and the 4th type has 2 variants, scara and spherical. These last two, scera and spherical, both have 2 revolutes and 1 prismatic joint, but their joint axes are aligned differently. In the case of the scera robot, all 3 joint axes are parallel. Hopefully you have enjoyed the tour of manipulators so far, and now it's time to begin exploring the mathematics needed to explain how they move. In order for a serial manipulator to be useful, it's essential that we know how the end effector moves in a 3D environment. Perhaps we would like to have the manipulator pick up an object from the assembly line and place it in a shipping container. Although it's very easy to think solely about the translation of the object from point A to point B in some XYZ coordinate system, manipulators have actuators that control revolute and prismatic joints, and the motion of these links can be highly nonlinear. Converting the manipulator's generalized coordinates into the position of the end effector is known as solving the forward kinematics problem. The first step to solving the forward kinematics problem is to see how to express vectors in different reference frames. A vector is a mathematical quantity that has both magnitude and direction. The concepts of magnitude and direction only make sense in the context of a coordinate or reference frame. For the purposes of this course, coordinate frame and reference frame are synonymous, and I will use the 2 terms interchangeably. Here, we have a 2-dimensional reference frame, A, that has orthogonal coordinate axes, AX and AY. A vector V in this reference frame extends from the origin to a point P. This vector could represent velocity, force, acceleration. It really doesn't matter. But for this example, let's assume that it represents the position of point P. Graphically, V can be expressed in terms of its components, that is, its basis vectors as follows, or as an equation. The coefficients Vx and Vy are called measure numbers because they measure how much of V is pointing in the direction defined by the unit vectors Ax hat and Ay hat. In other words, Vx and Vy are the magnitudes of V acting in the Ax and Ay directions. So the question is, how do we determine numerical values for the measure numbers? Well, we project V onto Ax hat and Ay hat using the dot product operator. The dot product of V and Ax hat is given by this expression. And since cosine is defined as the adjacent side over the hypotenuse, you can see that the measure number, Vx, is equal to V times cosine theta. What you should recognize, however, is this. There is nothing special about the A-frame shown here. Its orientation is undoubtedly the one you are most accustomed to seeing, but it is not unique. I could have just as easily drawn a coordinate frame like this. Is the vector V in any way different relative to this new coordinate frame B? No. It has the exact same magnitude. Clearly the measure numbers of Bx hat and By hat are different than the measure numbers in the A-frame. You can see this most easily by comparing the Y values and noticing that the blue frame has a smaller Y value. If you understand this much, then the next topic I'm going to show you, rotation matrices, is just a slight extension of what you've seen here. To understand rotation matrices, the main thing you need to remember is all we are doing is projecting vectors expressed in one frame onto some other frame. Rotations in 3D, although more difficult to draw, are fundamentally no different than the 2D case. The process still involves projecting the basis vectors of one frame onto those of another. In general, rotations can be performed about any arbitrary vector. However, when a rotation is performed about an axis of the coordinate frame, as is usually the case, such a rotation is often referred to as an elementary rotation. Let's consider 2 frames, A and B, that are initially aligned. Frame B is then rotated about the AZ axis by an angle theta. I will go through this example thoroughly, and then you can derive the matrices for rotations about the X and Y axes on your own. As we did in the 2D example, to derive the relationship of the B frame with respect to the A frame, we project the basis vectors of frame B onto frame A. As a reminder, the equation for the rotation between A and B looks like this. I personally find it easiest to build the rotation matrix one row at a time by projecting the B frame onto AX hat, and then the B frame onto AY hat, and finally onto AZ hat. The vectors used throughout this example are unit vectors and should be verbally described as AX hat, AY hat, etc. For the sake of convenience here, I'll commit the sin of referring to the unit vectors without explicitly saying hat every time. So let's get to it. You can work with the 3D view shown on the left, or, if you prefer, pretend that you're looking down the positive z-axis, so you only see the 2D xy plane. The first term in the rotation matrix is AX dotted with BX. Since the basis vectors for both reference frames are all unit vectors, this is simply equal to cosine theta. I'm going to belabor this point a bit just to make sure you're getting the concept. BX is the hypotenuse of a right triangle, and AX dotted with BX is the leg adjacent to angle theta. Remember, cosine is defined to be the adjacent divided by the hypotenuse. Now, since BX is a unit vector, that is, its magnitude is 1, then AX dotted with BX is just cosine theta. Now let's look at AX dotted with BY. That component is shown here. Or equivalently, you can think of AX dot BY being here. I think it's a little easier to see, particularly in the 2D view, that this is the opposite side of a right triangle. So AX dotted with BY is equal to minus sine theta. Again, the minus sign is because the projection falls onto the negative AX axis. And to finish out the first row, we have AX dotted with BZ. This is an easy one. We can see that BZ is orthogonal to AX. By definition, the dot product of two perpendicular vectors is 0. On to row 2. Row 2 is the projection of the B frame onto AY. Here is AY dotted with BX. It is the opposite leg of the right triangle. So this term is equal to sine theta. AY dotted with BY is the adjacent leg of the right triangle that has BY as its hypotenuse. So this value is cosine theta. And now all the hard work is done. AY is orthogonal to BZ. So AY dot BZ is 0. Row 3 is the projection of BZ onto the A frame. Clearly, BZ is orthogonal to both AX and AY. Thus, the first two columns of row 3 are also 0. Finally, AZ and BZ are coincident and their dot product is equal to 1. And there you have it, the rotation matrix between frames A and B. Before moving on, I suggest that you check that it satisfies the conditions of a valid rotation matrix. Good luck constructing the matrices for elementary rotations about the x and y axes. So far you've seen single elementary rotation matrices in 2 dimensions and 3 dimensions. A logical extension then is to describe sequences of rotations, a topic referred to as the composition of rotations. Let's look at an example. The image before you shows a sequence of 2 extrinsic rotations in 3-dimensional space. First is a rotation about the y-axis, and then about the original z-axis. The resulting image on the right is the composition of these 2 rotations. One system to describe a sequence of rotations is called Euler angles, named after the Swiss mathematician Leonhard Euler. According to Euler's rotation theorem, the orientation of any rigid body with respect to some fixed reference frame can always be described by 3 elementary rotations in a given sequence. For example, to achieve the orientation of the image on the right, the object on the left can be rotated about a fixed x-axis, and then about the fixed z-axis, and finally about the fixed y-axis. Before we dive into the mathematics behind compositional rotations, it's important to talk about several properties. There are, in fact, numerous conventions regarding Euler angles, so you must be sure to identify which convention is being used. To completely identify a particular convention, the following properties must be specified: whether it is a Tate-Bryan or classic convention, the rotation order, and whether it is a sequence of intrinsic or extrinsic rotations. This is often referred to as body fixed or fixed axis rotations. Let's start off with Tate-Bryan versus classic convention. In the Tate-Bryan convention, each elementary rotation is performed about a different Cartesian axis. The second property that we must specify is rotation order. Rotations are a non-commutative operation. Thus, the order in which rotations are performed matters. A rotation about the y-axis, followed by a rotation about the z-axis, will not generate the same result as rotating about the z-axis first, followed by the y-axis. In the following animation, for this reason, the order of rotations applied must be specified. Lastly, it's important to specify whether the rotation is an extrinsic or intrinsic rotation. Extrinsic rotations are performed about the fixed world reference frame, and in the literature are often referred to as fixed axes rotations. In an intrinsic system, each of the elementary rotations are performed about the coordinate system as rotated by the previous operation. Here are two visuals to help you understand the difference between extrinsic and intrinsic rotations. In this example of an extrinsic rotation, you can see the first rotation occurs about the y-axis, followed by a rotation about the z-axis of the fixed reference frame, not the new z-axis. In this example of an intrinsic rotation, the first rotation is about the y-axis, followed by a second rotation about the new z-axis. Since Euler angles are a sequence of 3 rotations, let's consider the composition rule for 3 intrinsic rotations. The first rotation is about the z-axis by an angle alpha, then about the y-axis by an angle beta, and finally about the x-axis by an angle gamma. Mathematically, we can express this in a very compact form with this notation. You would read this as z-y-x rotation from frame A to frame B. Since this is an intrinsic sequence of rotations, the elementary rotations are post-multiplied. Multiplying this out yields one somewhat complex-looking 3x3 matrix. Don't worry, you don't need to memorize the individual terms of this matrix. The important takeaway is that for intrinsic rotations, subsequent elementary rotations are post-multiplied. In the case of the same zy-x Euler angle set for extrinsic rotations, subsequent elementary rotations are pre-multiplied. Once again, multiplying the matrices out, we get a very complex looking result. Comparing the resultant rotation matrices for intrinsic and extrinsic rotations, we can see that the two are not equal to each other. In fact, I think this is a point worth repeating. Rotations do not obey the commutative law of multiplication. That is, the order of matrix multiplication matters. DH parameters are a topic that most students find confusing at first. And although there is an algorithm to assign frames, you will find there is still a fair amount of free choices to be made. It takes a bit of time and practice to learn, so don't worry if it seems hard right now. I'm going to show you how to derive the DH parameters for one common industrial robot called the Scara. Here is a schematic of the manipulator and its DH parameter table. An example of an actual Scara robot is the KUKA KR10. Scaras are characterized by having a revolute, prismatic, revolute, or RRPR structure with all joint axes being parallel. These manipulators are ideally suited for pick-and-place and fine assembly type tasks. One thing that will make your life much easier is to always draw the schematic in a configuration such that all the revolute joints have 0 angle and all prismatic joints have 0 displacement. Step 1 in our algorithm is to label all the joints from 1 to n. Here we go. 1, a revolute. 2, another revolute. 3, prismatic. And 4, revolute. Step 2 is to label all the links 0 to n. The fixed base link is always link 0. Here's link 0. 1. Notice that links do not have to be straight line segments. They can be curved or angled rigid bodies. 2, 3, and the end effector is number 4. Step 3 is to draw lines defining all joint axes. The dotted lines represent the joint axes. And to be clear, the axes of joints 3 and 4 are coincident. Step 4 is to define the common normals between joint axes. You can see that all the joint axes are in fact parallel, and joints 3 and 4 are coincident. So there are, in fact, infinitely many possibilities between each joint pair. As always, whenever there is freedom to choose, look for ways to minimize the number of non-zero DH parameters. Here's my choice for the common normal between joints 1 and 2, and for joints 2 and 3. So what about between links 0 and 1 and links 3 and 4? Both of these are special cases, which I will discuss momentarily. For now, let's move on to step 5, assigning the z-axis of frame I to point along the ith joint axis. The line of action for each joint has already been defined, but now you must decide whether the positive z-axis should point up or down. To be honest, it doesn't matter. You do what is most intuitive. In many applications, it's conventional to define positive rotations to be counterclockwise when viewed from above. So to stick with this convention, I choose positive z1 to be up. The same logic applies to z2. Joint 3 is prismatic. It feels natural to think of positive displacements as up, so I choose z3 up. And if I assign z4 as up, as you will see, the twist angle between z3 and z4 will be 0. This is an example of practice and experience being helpful that I alluded to at the beginning of the lesson. Step 6 is to define the positive x-axis for all the intermediate links, that is, excluding the base and end effector. For z-axes that are parallel, the positive x-axis should point along the common normal from zi minus 1 to zi. So here is x1, x2, and x3. Technically, x3 can be oriented in any direction that is perpendicular to both z3 and z4. You could think of this as a circular ring around the z-axis, but again, experience tells me that if I can make things parallel, in this case, x3 parallel to x2, it usually makes more DH parameters 0. But why did I put x3 down here? Well, I need to capture the translation of the prismatic joint, but any point along the z3 axis would suffice. I'm actually thinking one step ahead. What I care about is the location of the gripper. If instead I were to place x3 here, then for the transform between frames 3 and 4, I would need an additional constant term, d4, and I don't want that. Step 7 is to assign the x-axis of link 0. The number of non-zero DH parameters can be minimized by always choosing x0 coincident with x1 when the first joint variable, here theta1, is 0, and always choosing z0 to be coincident with z1. And finally, step 8, assigning the x-axis for link n, the last link. Here, you always choose xn to be in the same direction as xn minus 1 when the last joint has a 0 angle or 0 displacement, depending on what type of joint it is. Thus, x4 is parallel to x3. I want to make one more comment before moving on to the parameter values. The total homogeneous transform we will construct relates the origin of link 0 to the origin of link 4. Notice that the origin of frame 0 is not physically connected to link 0. So if you were really interested in knowing the transform relative to some point on the actual fixed base, then you could move x0 down to that point, at the cost of introducing one or more non-zero DH parameters. Now it's time to fill in the table. Remember, each row is the transform from link I-1 to link I. If your DH parameters are correct, then a basis vector of link I-1 should be coincident with the corresponding basis vector in link I after the homogeneous transform is applied. For example, x0 should map to x1, and z0 should map to z1. For I equals 1, we are considering the transform between frames 0 and 1. Alpha 0 is the twist angle between z0 and z1, measured about x0 in a right-hand sense. A0 is the distance from z0 to z1, measured along x0. Well, z0 and z1 are collinear, which is very convenient because for collinear axes, alpha and a are always 0. The link offset, d1, is the signed distance from x0 to x1, measured along z1. Again, we have collinear axes, which makes d1 0. Joint 1 is a revolute, so theta 1 is the only non-constant term in row 1. It measures the angle between x0 and x1 about the z1 axis in a right-hand sense. Since x0 and x1 are parallel when theta 1 equals 0, this term is just theta 1. Here's an important point. You may run into cases where the two x-axes are not parallel when theta is 0. If so, the theta term would be theta plus whatever the non-zero but constant offset happens to be. So be aware of that. Let's move on to I equals 2. That is, the transform between frames 1 and 2. Z1 is parallel to Z2. So alpha 1 is again 0. A1 is the distance from Z1 to Z2 measured along x1. Here's A1. To find the actual numerical value for A1, you would have to consult the manufacturer's specs or appropriate joint origin tag in the manipulator's URDF file. D2 is the signed distance from x1 to x2 measured along Z2. Since x1 is collinear to x2, D2 is 0. Joint 2 is another revolute, and in fact, the same logic applies as you saw in joint 1. Therefore, theta 2 is just theta 2. On to row 3. Z2 is parallel to Z3. This makes the twist angle, alpha 2, equal to 0. A2 is the distance between Z2 and Z3, measured along x2. D3 is the signed distance from x2 to x3, measured along Z3. Notice that to get from x2 to x3, you have to move in the negative Z3 direction. Joint 3 is prismatic, which means D3 is the only variable in row 3, and thus theta 3 is 0. Finally, row 4. This is similar to the transform between links 0 and 1, because I again define frame 4 to be coincident with frame 3 when theta 4 equals 0. As a result, alpha 3, A3, and D4 are all 0, and theta 4 is just theta 4. Congratulations! You made it through a very long and difficult concept. Now go outside and stretch your legs. You definitely deserve a break. Well, that's it. You now have all the theoretical background you need in order to complete the Pick and Place project. So let's recap what we covered. First, we saw that reference frames are a really big deal. They allow you to express vectors in whichever frame is most convenient or intuitive to use. But the use of multiple frames motivated the need for establishing systematic relationships between the frames that, in the most general sense, differ by a translation and arbitrary rotation. The homogeneous transform provided a compact and computer-friendly way of converting between frames. Further, the Dinovit-Hartenberg convention provided a systematic method for assigning a reference frame to each link. All of this was done to enable us to solve the forward and inverse kinematics of serial manipulators.
Almost every day, our lives are touched by various robots in a subtle way. The cars we drive are for the most part assembled and painted by robots. Most snacks we eat are processed and packaged by robots. When you order something on Amazon, your order is handled by more robots than humans.
Exactly. From generating a pick list to actually moving shelves with target product to the packaging station, robots take care of most tasks in a warehouse.
Wait, moving whole shelves?
Indeed! Yet one of the reasons why a company like Amazon still needs people is to pick things up off those shelves and put them into shipping boxes, and to restock shelves as necessary. It turns out these tasks that humans find relatively simple actually require complex solutions when it comes to robots.
In order to successfully pick and place an object in a semi-unstructured environment, the robot needs to identify the target object on the shelf, plan and perform a clean movement towards the object, and finally, efficiently grasp the target object without disturbing other objects. To motivate the advancement of these steps, Amazon organizes the Amazon Robotics Challenge every year.
In this project, you'll solve a part of the puzzle by using your knowledge of kinematics to perform a pick-and-place exercise, just like the Amazon Robotics Challenge.
Sounds exciting. Are you ready? Now that you are more familiar with Gazebo, let's move forward. First, we will launch Gazebo from our terminal by simply typing in Gazebo. Once it has loaded completely, you should see something like this. Be advised though, sometimes Gazebo has a tendency to get stuck in a seemingly infinite loading loop. If Gazebo does not fully load in about a minute, consider closing it by pressing Ctrl+C. Alright, moving forward. The Gazebo GUI is divided into 4 major sections: the scene, the side panel, the toolbars, and the menu. The scene is where you'll be spending most of your time, whether you are creating a simulation or running one. While you can use a trackpad to navigate inside the scene, a mouse is highly recommended. You can pan the scene by pressing and dragging the left mouse button. In addition to that, if you hold down the Shift key, you can also rotate the view. You can zoom in or out by using the mouse scroll, or by pressing and dragging the right mouse button. Next, we have a toolbar at the top. This toolbar provides quick access to some of the cursor modes, geometric shapes, and views. Simple shapes. You can insert basic 3D models like cubes, spheres, or cylinders into the scene. Select mode. This is the most commonly used cursor mode, and this is the one that allows you to navigate the scene. Translate mode. The translate mode cursor allows you to change the position of any model in the scene. Simply select the cursor mode and then use the proper axes to drag the object around until you're satisfied. Rotation mode. Similar to the translation mode, this cursor mode allows changing the orientation of any given model. Scale mode. This mode allows changing the scale and hence the overall size of any model. You can also add different light sources like spotlight, point light, or directional light to the scene. View change. This is a pretty useful tool. This tool lets you view the scene from different perspectives like top view, side view, front view, or bottom view. You can also hit the home button to get back to the home position of the camera. The left panel has 3 different tabs: World, Insert, and Layers. The World tab displays all the lights and models currently in the scene. By clicking on individual model, you can view or edit its basic properties like position and orientation. You can also change some of the physics properties of the scene like gravity or magnetic field via the physics option. Finally, the GUI option provides access to the default camera view angle. Insert tab. This is where you'll find all the objects and models to be added to the scene. You can left click to expand or collapse a list or directory of models. To place an object in the scene, simply left click the object of interest. This will bind the object to your mouse cursor. Now you can place it anywhere in the scene by left clicking again at your desired location. Layers. This is an optional feature, so this tab will be empty in most cases. To learn more about layers, check out the link in the description below. Bottom toolbar. The bottom toolbar has a neat play and pause button. This button allows you to pause the simulation for conveniently moving objects around. This toolbar also displays data about the simulation, like the simulation time, the real time, and the relationship between the two. There is also an FPS counter that can be found to gauge your system's performance for any given scene. Once you have properly set up your environment and successfully built the project, you are all set to test the pick and place simulator demo. First, make sure that the simulator is set to demo mode by checking that the demo flag is set to true in the inverse kinematics.launch file. Details can be found in the description. Now you can launch the project by using the handy Safe Spawner script. Once Gazebo and RVs are up and running, make sure you see the following objects in the Gazebo world: our robot, the shelf, our blue cylindrical target, and the drop box right next to the robot. We can now begin the demo. We just need to click on the next button on the RVs window to proceed from one state to another. Notice how a neat little status message is displayed on top of the robot in the RVs window. This status message changes as we move through different stages of simulation. Right now, it's just a simple welcome message. First, the robot is in the idle state. Clicking next will create a plan for the robot from the idle position to the target location. This also displays the plan. Clicking on next again will begin the robot motion towards the target location. Note that in the test mode, your code will be responsible to perform this motion. Once the robot reaches the target location, hitting the next button will perform a reaching movement. Next, the gripper will close to grasp the target object. Once the object is grasped, we can hit next to retract the arm and then plan for a motion towards the drop-off location. In a similar fashion as before, the trajectory to the drop-off location is displayed. Next, the robot starts motion towards the drop-off location. Again, note that in the test mode, your code will be responsible for this motion. Once the robot reaches the drop-off location, we can finally open the gripper and drop the target into the bin. This signifies the completion of a single pick-and-place operation cycle. Note that the planning framework creates a new plan with a different trajectory every single time, even if the object is spawned at the same location. In addition, you can also control the spawn location of the target in the shelf. You can find the details in the description below. Feel free to play around with this demo, especially with different target locations, to get a better understanding of all the steps involved. Especially, pay attention to the part that your code needs to perform.
In this video, I present a walkthrough of the forward kinematics of the KUKA KR210 serial manipulator. The KR210 is the robot arm used in the pick-and-place project. The first major challenge in this project is to sketch the robot arm in its zero configuration. In other words, the schematic you draw should be representative of the KUKA arm's pose when you first spawn the robot in simulation. Here is a top view of the KUKA arm in its initial pose. I have made the arm semi-transparent by setting the alpha value equal to 0.3. By convention, the URDF file should define the pose of the robot when all joint variables are equal to 0. If you add the axis topic in RViz, you see that the arm essentially lies in the XZ plane. The x-axis is indicated by the red cylinder in this image, the y is green, and the z is blue. To construct the DH parameter table for the manipulator, begin by labeling the joints from 1 to n. In this case, n equals 6 because there are 6 joints. Next, draw lines defining each joint axis. Just to be clear, joints 2, 3, and 5 are all parallel. Joints 4 and 6 are coincident. Then, label each link from 0 to n. The next steps are to define directions for the positive z-axes and then x-axes. The x-axes define the common normals between zi-1 and zi. The origin of frame I is defined as the intersection of xi with zi. Now, the point we ultimately care about is the center of the gripper, so I will add an extra frame that is rigidly attached to link 6. Here is the location and orientation of the gripper frame. As you can see, it differs from the reference frame of link 6 only by a translation along the z6 axis. Next, I show the location of each non-zero link length, the a's, and the link offsets, the d's. ai-1 is the distance from zi-1 to zi measured along the xi-1 axis. Thus, a1 is the distance from z1 to z2 measured along the x1 axis. d sub I is the signed distance between xi-1 and xi measured along the zi axis. Therefore, d1 is the distance between x0 and x1 measured along z1. The twist angle alpha I sub 1 is the angle between zi minus 1 and zi measured about the xi minus 1 axis according to the right-hand rule. If the two joint axes in question are parallel, such as the case between z0 and z1, then the twist angle is 0. Now the question is, how do we get numerical values for the a's and d's? Well, that comes from the URDF file. The URDF's file name is kr210.urdf.zacro, and it's located in the URDF folder. URDF files are very verbose and contain many parts that we don't need to worry about right now. The most relevant section to your problem begins under the joints heading. Here, all the movable joints are defined. For example, take a look at lines 322 to 327. This block of code identifies joint 1 as a revolute, rotating about its z-axis, and it connects the base link to link 1. The origin field defines the position and orientation of the joint relative to the parent link. But you also need information about the gripper frame that's rigidly attached to link 6. Here is the relevant code block. As you can see from lines 202 to 206, the origin of the gripper joint is 0.0375 meters in the x direction relative to link 6 and has the same orientation. The gripper joint is also a fixed joint, meaning there is no relative motion between it and its parent link, link 6. Now pay close attention to what I'm about to tell you. The thing you must recognize is that, in most cases, the joint origins in the URDF file are not consistent with the frame origins created in accordance with the DH parameter convention, nor do they have the same orientation. Unfortunately, you can't directly display joint reference frames in RViz. If you turn the robot model off, the reference frames you are able to see are actually the link reference frames. Here, I show the joint reference frame origins, indicated by black triangles, and orientations as they appear in the URDF. To keep the drawing from being horribly cluttered, I only show the origins of the DH parameter frames as a point of comparison. The other thing you need to recognize about the URDF file is that each joint is defined relative to its parent. For example, to get from joint 1 to joint 2, you have to translate 0.35 meters in the x direction and 0.42 meters in the z direction. One thing you should do as you solve this problem is verify that the transforms make sense. Each row of the DH parameter table represents the homogeneous transform between frame I-1 and frame I. In your Python code, you should incrementally check that the position of your reference frame origins are consistent with the cumulative displacements defined in the URDF file. Since the KR210 has 6 revolute joints, only the theta terms are time variables, and most of them are straightforward. The only tricky one is joint 2. Remember, the definition of theta sub I is the angle between xi-1 and xi measured about the zi axis in a right-hand sense. The manipulator was drawn in a configuration with all joint angles were assumed to be 0. But in this case, x1 is not parallel to x2 when theta 2 equals 0. There is a non-zero but constant offset of minus 90 degrees. Finally, in order to compare the total homogeneous transform between the base link and the gripper link, we need to account for the difference in orientation of the gripper link frame. The easiest way to do this is to apply a sequence of body fixed, that is, intrinsic rotations to the gripper frame in your Python code. In order to get the two frames to align, you can first rotate about the z-axis by 180 degrees, and then about the y-axis by an angle of minus 90 degrees. Let's take a look at some Python code. We begin by importing numpy and sympy and all the functions that we will need. Next, we define symbolic variables in sympy for use in our DH parameter table. We then establish a dictionary of our known DH parameter quantities, where alpha represents the twist angles, A represents the link lengths, D represents the link offsets, and Q represents the joint variables. the thetas. Next, we create homogeneous transforms between individual neighboring links. For example, between link 0 and 1, 1 and 2, 2 and 3, all the way between link 6 and the gripper G. Next, we begin to incrementally build the total homogeneous transform between the base link and the gripper frame by incrementally post-multiplying individual homogeneous transforms. Next, we need to account for the difference in orientation of the gripper link as it's defined in the URDF versus the DH convention. We do that by first applying a body fixed rotation about the z-axis and then about the y-axis. So this R sub correction is the composition of rotations of this z-axis and y-axis rotations. And this should give you the forward kinematics of the KUKA arm. And we can check this by evaluating the total transform between the base link and the corrected gripper length by evaluating the matrix at some arbitrary joint values and see if it matches the translation component of the end effector from Ross. Well, what's left is to actually solve the inverse kinematics portion of the project. The general process is outlined here, but you should review the pick and place project instructions and lesson notes for the details. Good luck!
Let's continue. Here we have the graph of KR210 manipulator. Before building the DH table, we need to first figure out the position of the joints. We need to use KR210's URDF file to get the values. This is the corresponding URDF file from the repository named kr210.urdf.zecro. As was said in the classroom, we only need to focus on the joints part starting from line 317 because that's where the joints are defined. Each joint has the property origin and axis. The origin tag defines the origin of the joint, and the axis tag defines the joint's axis. Notice that the RPY value of KR210's joints are all 0, so there is no rotation between the reference frames, and it will be relatively straightforward to find out the translation between reference frames in URDF. I pick out the XYZ values we need from the URDF file and mark the lengths on KR210. You could refer to this graph later when populating the DH table. Now that we have the URDF values in place, I would like to have a brief review of the DH table before building it. This is mainly covered in the lesson Danovet-Hartenberg parameters. We need the DH table for kinematics calculation. We will be using a modified DH table based on Crick's convention. This will be different from traditional DH tables, so please pay attention to the value and subscript. First, let's recap the principles of arranging reference frames. Z-axis is the direction of the joint axis. X-axis is parallel to the common normal of Z-axis. If the Z-axis are parallel, we have no unique common normal. There are 4 parameters in the DH table: alpha, A, D, and theta. Let's go over it one by one. The link length AI-1 is the distance of ZI-1 and ZI, the neighboring axis along the common normal XI-1. Link offset DI is the length of the common normal between XI-1 and XI along ZI. If OI is on XI-1, then there is no offset. The value of DI will be 0. Next, we will talk about alpha and theta. Alpha is the twist angle, which is the angle of z-axis about the common normal, usually x. As to theta, for revolute joints, it is the angle of the joint, which would be a variable. The definitions are a lot to swallow at once, so I will walk you through populating the DH table. Moving on to populate the DH table. This is the arrangement of reference frames, following the principles in the classroom. Again, Z-axis is the direction of the joint axis. X-axis is usually the common normal of Z-axis. First, the values from O0 to O1. A0 is the distance between Z0 and Z1. As the axes are coincident, A0 is 0. Similarly, alpha 0 is 0 as there is no twist angle. For D1, there is an offset between x0 and x1 along Z0 axis. The value on Z-axis from O0 to joint 1 is 0.33, and the value on Z-axis from joint 1 to O2 is 0.42. Summing these values yields 0.75 as our D1. Theta 1 is the joint variable, and we will use the variable Q1 for it. Keep in mind that we are using modified DH parameters, so instead of alpha 0, A0, D0, Q0, we are using alpha 0, A0, D1, and Q1 in our first row. Next, let's evaluate O1 to O2. A1 is the distance between Z1 and Z2. The common normal is x1 axis. From the graph, it should be the value of O1 to O2, which is 0.35. This time, there is indeed a 90-degree twist angle from Z1 to Z2. Alpha 1 is minus 90 degree following the right-hand rule. There is no offset from x1 to x2 along Z1 axis. Thus, D2 is 0. Theta 2 is the joint variable of joint 2. Unlike other joints where the x-axis are parallel, there is a 90-degree difference in x1 and x2. We need to compensate it by subtracting 90 degrees from theta 2, which is the angle between x1 and x2 around Z2 axis. Moving forward to O2 and O3. A2, the link length, is the distance between the joints, 1.25. The twist angle alpha 2 is 0 as Z2 and Z3 are parallel. The offset of joint axis D3 is 0 as O3 sits on x2. Now O3 to O4. We need to observe that O4 is actually on joint 5. In fact, O6 is also on joint 5, and this is the wrist center that was described in the classroom. The link length A3 is the sum of 0.96 and 0.54, which are the distance along x0 from joint 3 to joint 5. The joint offset D4 is minus 0.0054. It is the distance between Z3 and Z4 along x3. The twist angle is the angle between Z3 and Z4 around x3 following the right-hand rule, that is the minus 90 degree. From O4 to O5 is quite straightforward. A4 and D5 are 0 as O4 and O5 are on the same point. The twist angle alpha 4 is the angle of Z4 to Z5 around x4, that is positive 90 degree. Similarly, from O5 to O6, A5 and D6 are 0 for the same reason. The twist angle alpha 5 is negative 90 degree from Z5 to Z6 around x5. In the end, from O6 to the end gripper, there is an offset of 0.303 along Z6, which is the D7. Nice job! Here is the DH table that we just completed from the URDF file and the reference frames. Each row represents a transformation from joint to the next joint. However, we still have one last thing to tackle. That is the orientation of the gripper. Let us examine our final gripper position. The yellow coordinate is the current gripper reference frame. It is apparently different from the original URDF reference frames, the green axis. It is in the same direction of the origin on the lower left corner indicated by x0 and z0. So we need a final matrix to align the two reference frames of the gripper by rotation. In the classroom, it is suggested to rotate about z-axis and then y-axis. Thus, we could have our R correction using these two rotations. We will then build the transformation matrix following the DH table as illustrated here. And here is the code block to build the transformation matrix from O0 to the gripper, also called an effector. Once we have the transformation, we could go on to calculate the inverse kinematics. Using the classroom content and algebra, you would be able to calculate the wrist center and complete the inverse kinematics. Here are the steps from the classroom to calculate the inverse kinematics of KR210. The inverse kinematics problem is decoupled to the inverse position determined by theta 1, 2, 3, and the inverse orientation determined by theta 4, 5, 6. Let's go through it one by one. Wrist center is calculated based on the gripper's location and the last link's length. Here is the formula that we used for the calculation. We backtrack from the position of end gripper along the gripper link to reach our wrist center, where is also 04, 05, and 06 lies. Now that we have our wrist center, we could calculate theta 1 to 3 using the geometric properties. Theta 1 is straightforward if we look from above to the robotic arm. It equals to a tangent to WCY, WCX. Then we'll work on theta 2 and theta 3. First, theta 2. Using the diagram from the classroom, we could first figure out the size and the angles of the triangle formed by joint 2, joint 3, and wrist center. Joint 2 to joint 3 is A2, that is 1.25. J3 to wrist center is 1.504, which is the actual length between J3 and J5. J2 to wrist center could be calculated using the position of wrist center. Don't forget to subtract the height of J2 from O0, that is 0.75 from wrist center's Z coordinate. For joint 3, we could identify the angle of theta 3 by subtracting the angle B and the angle between joint 3 to wrist center and joint 3 to joint 4. The value is A tangent 2, 0.0054, 1.5. Thus, theta 3 equals to pi over 2 minus angle B minus A tangent 0.0054, 1.5. Now, let's move on to inverse orientation. What we have now is the matrix R0 to 6 and the matrix R0 to 3 determined by theta 1, 2, and 3. We could acquire R3 to 6 by multiplying the inverse of R0 to 3 to R0 to 6. The result, R3 to 6, as RXYZ, accounts for the rotation of the end gripper from the wrist center. As R3 to 6, which is the RXYZ here, we could solve for alpha, beta, and gamma in this equation, that is our theta 4, 5, and 6. Here are the formulas used to calculate the theta values. Now you have completed the hardest part of kinematics analysis. Continue your work testing your ikserver.py in ROS and complete the pick and place project. And I will go through the ikdebug.py file for you to connect the walkthrough with the actual code.